have many billboards in Thailand, and it's always collapsed when it's hit by severe thunderstorm. Okay. Now, before showing you the wind tunnel test, let me give you a rough explanation about the concept of aerodynamics, how the wind can produce force, okay, the wind force. So you look at the picture on the left, solid body. You can think of this as a building. Before you have the wind, the pressure, air pressure outside is about atmospheric pressure. Air pressure inside the building is also equal to atmospheric pressure. But when the building is subject to wind flow, as shown in the picture, it will create higher pressure on one side, on some side. It will create a pressure lower than atmospheric pressure in other side. For the side that have higher pressure, we call this just pressure, positive pressure. For the side that you have lower pressure compared to atmospheric pressure, we call this negative pressure or suction. Okay? So you have the wind pressure force pushing the building or pulling the building. And if you integrate some of this force, pressure force around the surface of the building, you will get the net force. The net force can be separated into the force in the direction of wind flow, we call drag. You can calculate the force in component in direction perpendicular to the wind direction, we call lift, or we can call it side force, and it's also create torsional moment to your structure. This is how wind produce the wind force or wind pressure to the structure. But you cannot see the wind. You cannot actually feel the pressure directly. So we need to have some facility to actually check and estimate all this wind-induced pressure and force. So the facility I mentioned is called wind tunnel. Okay? It's a facility that creates the wind flow inside the tunnel. And you can actually adjust the property of wind to be similar to natural wind. We call boundary layer wind flow. Okay? This is our wind tunnel produced by AIT and Thammasat, another university. We work together to develop this wind tunnel. So it's a kind of long length wind tunnel. We can put a scaled down model of the structure inside this tunnel. So we can actually measure the wind-induced pressure. We can measure wind-induced force, wind effects, and other wind effects by using this kind of wind tunnel. I give you some idea how we use this wind tunnel. Let's start from a structure like this. We call large billboard structure. This structure has a very large surface area, so it's quite exposed to wind pressure. The design of the structure will be controlled by the wind load. So if you have accurate wind load, then you can ensure the safety of this structure. But if your information about wind load is not realistic, then the structure might be in danger. Okay? Your design may be not conservative enough or under conservative. So the structure like this may have a size of 30 meter high, 30 meter wide, but then when we put into the wind tunnel, it's become 30 centimeter height, 30 centimeter wide, it's become smaller. This is a scaled down model of wind tunnel. And we put, we drill many holes into the panels on both sides, and we connect this hole to plastic tube on one end, and we connect the other end of plastic tube to our pressure sensor. Okay? So by this way, you can actually measure pressure at many different locations on the panel. Okay? These points are called pressure tab. And we can put the pressure tab on both on two sides. So you can see how wind pressure vary with the location, with the time. Okay? Let me show you an example. This is a result from the measurement. If the color is yellow, it means the pressure is all equal to atmospheric pressure. If it's on orange or red, it's higher than that. If it's green, blue, it's lower than atmospheric pressure. So this is a net pressure coming to side. So you can see that wind pressure is not static pressure. It's dynamic pressure. It's fluctuating all the time. Sometimes large, sometimes small. Okay? The wind direction is perpendicular to this panel. This time is heavy pressure on the right-hand side. Now, in the next time instant, it may be heavy on the other side. Okay? So actually it's not uniform and it's not static. In the design, if you follow building design regulation or code, standard code, you may come up with a picture of pressure on the right, on the left-hand side. The code will give you, say, uniform design pressure to design this structure. But this is not realistic. For uniform pressure, your net force will be at the center. Your two columns will share the load equally. Okay, but in reality, the pressure may be heavy on the left side, and another instant may be heavy on the right side. So it will create kind of eccentricity to the panel. Like in this picture, maybe it's heavy on the left-hand side column. So the load maybe all go into the left column, not on the right column. So if you design with unrealistic wind pressure, your structure may not be safe. It may collapse when it's hit by this windstorm. So I give you some example of modern design standard. This is the standard in Thailand. I can show this because I'm the code writer. So I make this by myself based on the wind tunnel test. So we have to consider uniform wind pressure distribution and also non-uniform pressure distribution. If you design the structure to be able to handle all these cases, then the structure will be safe. Okay? So this is a kind of how we come up with the design pressure in the wind design standard. We have to conduct wind tunnel tests, understand the nature of wind pressure, and use that, translate that into the code. Good thing about wind tunnel model test is you can actually check the wind load on very complex form of the structure. This is an example. It's a 40-meter tall Buddha statue located in the western part of Thailand, Kanchanaburi province. We put this scaled down Buddha image on top of wind tunnel, on top of turntable. So you can turn this model into many different directions. The wind always comes in one direction, but you can change the orientation of structure respect to the wind direction. So we can check the wind load for different attack angle, different direction of wind compared to the structure. So this shows an example. The horizontal axis shows the wind direction from 0 to 360 degrees is one round. And the vertical axis shows the normalized drag coefficient, which is related to drag force, and normalized lift coefficient related to side force. And you can see the pink color zone is for drag force. You have upper bound, lower bound, and the mean value. The blue color is side force, acting on this Buddha statue. So when we conduct this kind of test, you have all this information in your hand. Structural engineer then can have good information about wind load to design their own structure. So when you combine this information with your finite element model, computer model of your structure, combined with the accurate wind load information, then you can estimate the response accurately. You can compare the result, the response, the stress in a member, bending moment in a member, shear force, we call demand, compared to the capacity. So you can find DC ratio. Actually, it's D/C, not DC, demand over capacity ratio. So we can use this wind load information together with our realistic computer model of a structure and come up with an accurate estimate of response in our structure member. So you can guarantee the safety of the structure. Now I move to the topic related to more on the tall building, because tall building is the main theme for this seminar. So let's look at a simple geometry like a rectangular shape, rectangular section, tall building with a uniform section over the height. Okay, you look at the right-hand side is a top view of this building. Wind coming from the right to the left, it will create the drag force, it will create the side force, it will create torsion to this structure. So you can see we have the four sides of this structure: the front, the back, the right, and the left. So the pressure are shown on the right, on the left-hand side, okay? And the force time history is shown on the top. Oh. Oh. Can you help running this animation? Click to that. Okay, thank you. Can you see that? You have pressure in the front, always positive. Pressure in the back, always negative. And if you sum positive pressure and negative pressure, the front and the back, you get the drag force. And you have pressure on the right and the left, and they are both negative, but sometimes it's heavy negative on the right, sometimes heavy negative on the left. So you have also the fluctuating force, side force as well. And all this pressure is not uniform, so it will create torsional moment to your structure. So you are not having only drag force. You have drag force, side force, torsion, all these force applying to your structure, okay? So drag force will create what we call the response in along wind direction. The side force will create what we call response in across wind direction. And then the torsion will create a torsional movement in your structure. So this is real. This is the real characteristic of wind load, which is quite complex. But engineers are trying to simplify this one into equivalent static force. Now let's look at the behavior of our structure. The top pictures show how the wind force vary with the time. We call drag force. It's sometimes high, sometimes low, because the coming wind characteristic is wind turbulence. It's boundary layer wind turbulence. It is not uniform. It's fluctuating wind velocity. So sometimes it creates high drag force, sometimes it creates low drag force. It varies slowly with the time. If your structure is a kind of mid-rise building with a high natural frequency, your structure is act more like a static structure. The response will be more like quasi-static. So when the force is high, you have high response, you have high deflection, you have high shear load, you have high overturning moment. When the force is low, you have low response, low deflection, low shear, low moment. Okay? But when the structure become a high-rise structure, the structure become more vulnerable to vibration. You have additional response we call resonant response. It's a kind of vibration of the structure on top of this response. Okay? So you see the different pattern. Not only vary with the wind load, but also you have a vibration on top of that. So this will add more, increase the deflection response, will increase the shear force, will increase the moment, and also it will create vibration effect to the people who stay inside the building. Okay? If the vibration is too high, it may create motion sickness problem to the people inside the building. This is an example of wind code in Thailand. When we made it, I have to look at many code and standard like National Building Code of Canada, AC7 from the US, AIJ standard from Japan, and Australian standard, New Zealand standard. So we look at all this as our model when we develop the code, and we know that they have a procedure to handle this effect. You can design tall building, consider the effect of turbulence load, wind, slowly fluctuating load, and the vibration effect. There's a procedure called gust response factor procedure. So we can handle this one if we follow the code and standard, modern one. I think in India, I have not checked yet, and you may have the similar standard to handle this. But what we found is most standard can have a guideline or design procedure for a long wind direction. Only some have a design standard for a crosswind direction, and only a few have a guideline for torsional effect. So, but if you conduct wind tunnel tests, you have all of this. You have all this direct information. And another point is, all these standards are for standalone building. They do not expect that you have big buildings nearby to your building that you design. So, but in reality, you may not have that condition in your project. This is example of wind-induced vibration on the top of the top floor of the building. So this is a normal requirement. If you meet this condition, you may need to have your the structure test in wind tunnel. Say if the building height is more than 150 meters, the dynamic effect is going to be significant. If you have complex geometry, then the code recommended pressure and load may not be applicable to your case. If you have complex topography around your building, or if you have a large building nearby to your structure. Okay? So these are the conditions that you may need to find actual wind load from wind tunnel tests. I show you some examples that meet that condition. This is one of the projects we have coming from Philippines. This is a 2 tower and located in the area where you have a small hill. So inside the wind tunnel, we have to create this small hill and nearby structure and topography. And you have to look at the tower. It's a twin tower. The presence of one tower will affect the wind load on the other tower. So you cannot just looking at them separately. So we have to put the model having 2 of them inside the wind tunnel. So this is showing some idea how we conduct the wind tunnel model test. We have to first produce the wind and pass it through some section that will create natural wind condition. We call boundary layer wind turbulence. But we have to make this boundary layer wind turbulence in a small scale, not large scale. we have to reduce the size of the wind about 1 to 200 times, 300 times. And then we create a model of our structure also in a similar scale, 1 to 200, 1 to 300, or 400, okay, with the presence of nearby structure. We put all this in a turntable so we can check the wind effect in different wind direction, okay, and normally we will conduct the measurement of structural wind load, the wind load to the main structure, and give this information to structural engineer to design the structure. We also measure the cladding pressure, the wind pressure on the surface, so that you can give this information for those who design the cladding panel and the structure that hold these cladding panels. Sometimes we also want to know the wind environment around the structure. I will explain this one, these three one by one. Okay, let's start from simple one. This shows you the measurement of cladding pressure or exterior surface pressure of the structure. So what you need to do, you look at the picture in the center. It's just the model of the structure. We have to simulate all the details, and we have to put many pressure taps into the surface, connect the pressure tap to the pneumatic tube, plastic tube, and connect this plastic tube to the pressure sensor on the right-hand side underneath the wind tunnel. Okay, the picture on the right, the one on the left is showing how we produce the model. We use 3D printing. We have a wind tunnel team that can conduct this kind of test. So they have to get the drawing from the client and then produce the model that will simulate the geometrical shape of the building by 3D printing. Okay, this shows you how we put the structure on turntable. You see that it's turning now, but when we conduct the measurement, we have to stop the turning. We have to lock it to some configuration and measure the pressure, and then we turn to the next wind angle. So we conduct this test maybe for every 10-degree change of wind direction. So we have to repeat the measurement maybe 36 times to complete the test. Okay, by this way you can consider all the wind direction. You can determine the positive pressure acting on all the surface of your building. And you can also get negative pressure on all sides of your building. Okay? So you can hand this information to those who design the cladding and the frame that support the cladding. All right? And if you compare with the wind code, wind design standard may give you design wind pressure. And wind tunnel test, you can also obtain design wind pressure. They may not look the same. In general, the code will be on conservative side, higher, but not always. We found that in some locations, the wind pressure from wind tunnel at some spot and some locations are also higher. Okay, so in general, you can save the cost because you get more realistic wind load, wind pressure for your design. So you don't have to make an over-design, make the cladding to be too thick in the area that you don't have high pressure. But the area that you have high pressure, then you can increase the thickness. You can increase the strength of the frame. So by conducting the wind tunnel test, you can save the cost of the building. You can reduce the cost of the building. But of course, there will be the cost for wind tunnel test. The cost of wind tunnel test is much lower than the cost that you will save by this accurate information of wind pressure. Now, this is another type of testing we call the testing to get the wind load for structure design. So this is an example of the model, and we put, if you see on the left-hand side, you see that we have force sensor at the base. This force sensor is a kind of, it can measure 6 components of force. Force in the drag force, side force, uplift force, torsional moment, overturning moment, all 6 components. It's a dynamic force sensor. Well, the sensor is very, very expensive, but it's actually quite convenient. We just attach the model to the force sensor and to the structure that we want to measure. Okay? This shows example. We get the force coefficient for all the wind direction. We have upper bound, lower bound, the mean value. Actually, we have more than that. We have the details how it fluctuates with the time. So we know frequency composition of the force. So we can use that. We call the spectrum of the wind load. Okay? But for the design engineer, we don't give this detail. We give the result in the form of equivalent static force, because most engineers, structural engineers, are familiar with equivalent static force. So we translate all this dynamic wind load into equivalent static force, and we give to structure designer. The wind tunnel testing team will not do structure design. We just provide the information, and we try to obtain the most accurate information for the engineers. But from this information, you can also estimate wind-induced vibration at the top of the building as well. Okay, this is show another example how we made this kind of model. The model must be made it light. Sometimes we use carbon fiber pipe as a center core and put on a force sensor. Don't worry about the equation. Okay, it's prepared by my assistant, so they like equations, but I don't like equations. Okay, after obtaining this, what you will get is equivalent static wind load in X direction, in Y direction, and you will have also moment, equivalent static moment load applied to your structure. So you can combine with dead load, live load, earthquake load, whatever you want in the design. So the design will be the responsibility of the structural engineer. But the wind tunnel team will provide a more accurate and reasonable wind load for your design. And this is comparing between the wind load obtained from wind tunnel tests and the wind load obtained from the code. Okay? So we compare by calculate the base overturning moment at the base of the building. We divide overturning moment obtained from the wind tunnel compared to overturning moment obtained from the code. If you get the 1, mean they are equal. Code force equal to the wind tunnel recommended static force. But sometimes we have higher than 1. Mean the real load is higher than what code say. But most of the time we have lower than 1. Mean the actual load is lower than what the code say. I forgot to say that the number on the horizontal axis show the project number. Mean this data is produced from 30 different projects. So some projects have higher load than the code load. Some have a lower load than the code recommend. So in general, you can save the cost of the structure as well. But in the case that you may have higher load, then you will know. And you have to ensure that your structure will be safe, have enough capacity against that load. I present yesterday about vibration control by June mass damper, so I'm going to skip this one. But from the wind tunnel test data, we can estimate vibration level, and we can estimate in terms of horizontal floor acceleration at the top. And we can use this information to check if we put June mass damper on the top, can we suppress it down? If we want to put viscous damper or some other vibration control device, we can try, because we have accurate dynamic loading for the structure. Here is another aspect that we can test, we call wind environment condition. Because of the presence of the building, it may create a strange flow effect. You may have a channeling effect that produce locally high wind velocity, and we will give an impact to the people in around the building. Okay. This is an example. This is the project I mentioned earlier in Philippines. The client may want to have an open air restaurant. They may want to use some area for recreation area, use as a park or some purpose. But if the wind speed is too high, you cannot do that. Okay, so we have to put the embedded a special type of sensor we call Irwin probe into the building model. Okay, this will allow us to check the local wind velocity at these particular locations. And we can compare the measurement of wind velocity with the criteria. If the wind speed is low enough, then you can use it for many purposes, for reading, eating, drinking. If the wind speed is too high, you cannot even walk carefully. You have to walk carefully. Okay, so there are variation in the application for different level of wind speed. So for example, for this project, we can identify that some location is the wind velocity is too high. It's too windy because it's just a spot between two towers and it produces channeling effect. The point is we will know this before we construct the building. So if you don't like that wind condition, then you can modify it before you construct the building. Okay, you can put some shield, you can plant more trees, you can modify other geometry to change the wind condition, and you can test again in a wind tunnel. Okay, you can just repeat this process, and it's cheaper than let it happen and correct them later. This shows you some ideas about the past project we have. Many of them are tall buildings. Some want to get the force, the structural load. Some want to get the pressure. Some want to have a wind environment study. Some want everything. Okay? And we also conduct the test for the bridge, for statue, for museum, many other forms of the structure. Well, I'm going to skip this one, but it's inside my presentation file, so you can take a look into details. This is a more detailed information about wind tunnel tests that provided by AT Solution team. Not only the wind tunnel test, but we have also other study like computational fluid dynamics, we call CFD simulation. This one is quite hard to obtain from wind tunnel test, so we can perform kind of the calculation, computer calculation of wind flow inside the building. So if you open the doors, you close the window, open the window, what happened to your circulation inside the building? We can do it by CFD simulation. Or you can look at wind environment around the building. Okay, all these are computed by computer. Okay, but I still think that it's not as reliable as wind tunnel physical model test yet. But it provides us more option to understand the wind effect. So now the time is up. So This is the last set. A few more slides. Okay. Okay. This is the future. In the past, up to now, we may treat wind load as equivalent static force. But I think you may have to start thinking of a different approach. This project is an example, is a kind of dome, about 86 meters in diameter. That's a picture. And the structure is a kind of complex 3D truss system frame to carry the load. And we put many pressure taps onto this one, so you can actually obtain dynamic wind pressure on the surface of this dome. Okay, what we did for this project is the wind tunnel team just measure the wind pressure load, and we hand all these dynamic files to the structure team. The structure team will have all dynamic loading information at different locations, and then they can calculate how the moment fluctuates, shear force fluctuates, uplift force. Because this day, your finite element model can do more than static load. You create finite element model, just let the program run. So you compute all this load by the software, okay? And by this way, you have more idea, understanding of the real behavior of the structure. We found that if you use a static load, there will be so many load combination cases that you have to consider, so complex. So better use the realistic load. It will be much easier, more direct, okay? This will be the future, okay? I think that's all from my side to give you just introduction to wind tunnel model test. Thank you very much for your kind attention.
That was a very, very important presentation from Professor Penang. I think wind loads play a very important role in the stability of structures, not only tunnels, but residential structures, high-rises, etc. So now to take the questions, we have Mr. Zia on the online platform, and Mr. Penang is also here. We will strictly take about 5 questions, one minute each for one question. Please do not make any interaction or appreciations. Let it be a very clear-cut question, and one person, one question, please. This is a request. Thank you so much.
Yeah, please.
Sorry, a small doubt, sir. Here.
Oh, okay.
So, the professor, the water moves in a wave motion. Water moves in a wave motion. Air also moves in a wave motion. But in the wind tunnel test, you are using not in a wave motion. It's a fan. Radial, you are having a test done.
I'm not clear about the question, but we produce the wind in the wind tunnel by have a fan rotating. The wind at first will look very highly turbulent, but we will let it go through some flow processing unit to clean up all this, to make the wind inside the wind tunnel become uniform, low turbulence. And then we start modifying that one to match with the real natural boundary condition. Because sometimes the buildings are located near to the sea. Sometimes it's in the city center. Sometimes it's surrounded by small town. So we have a different wind condition. We can produce that in a wind tunnel.
Sir, these size effects, now you are doing it in a small model, the wind test. So to get that size effects corrected, what are the measures you are taking, sir? That is wind velocity you are changing, or what is exactly you are doing to take the size effects?
Yeah, yeah, that's a key point in the wind tunnel test. We have to scale down the size of from the real building to very small model. So we have to observe, make sure that it's similar to the reality. So there are many similarity requirements in conducting the wind tunnel. But fortunately, we can meet all of them if we make a proper design of a model. But it takes time to explain this one. Okay? I can explain, but not now.
Thank you.
Hello, sir. Good morning. Here in this side, sir.
Okay.
What is the effect of the wind on moving vehicle, sir?
Effect of what?
On moving vehicle.
A moving vehicle.
It is also going at 100 kilometers speed.
I think this is maybe related to the design of bridge or roadway. But normally, when the wind speed is too high, you have to stop the traffic. Okay? But if you want to know how the wind can induce a load on moving vehicle, it can be tested as well. It can be tested in a wind tunnel as well. But we have never conducted that. Yeah.
Okay.
I have never conducted it. But
Thank you.
Good morning. So my question is regarding the two aspects. One is the wind effects on a dome, which you showed just now, and also wind effects, I think, on a dome, circular structure.
the dome.
Dome, yeah.
Okay, can you bring back the presentation? Go to the last slide. Okay.
Second last.
Okay.
The one
Go.
before this.
Yeah,
Yeah.
this one.
Has this resulted in anything for the code? Because this is a very vital information. And has it got into your code, and has it got into any other statutory body?
No. I think this structure is called long span roof structure. Dome or long span roof system. They have so many different configurations. So it's difficult to find a typical shape. So we do not include that in our code or standard.
No, there have been publications on this in London, but from your results, I see a little different configuration. So this has to get into a code somewhere, right, for design?
They may have a code recommended pressure for some simple shape, like circular shape or something. But this is kind of dome with it's a monk bowl shape. In a Buddhist monk, they have a bowl that they carry in the morning. It's made in a Buddhist temple in this form. So we cannot find the recommended pressure in any code or standard. So we have to create by ourselves.
If permitted, one more question on the same thing. The previous slide, or the next slide is, I think, more pertinent to your PEB structures. You know, the next one.
Next one.
Yeah. The next slide to this, yes. This would be more pertinent to all the PEB structures that come along. Here also there's a parameter of X, Y, I mean, whether it's a rectangle or it's a square and things like that. Because this is very interesting that you have done this work. It's going to be useful for PEB.
Yeah. It will be used, can be used for performance-based design.
Yeah.
Like what Mr. Ong presented yesterday. You have more accurate and detailed wind load information.
Yeah.
You just put that into your computer program.
Yeah.
And you can get it right away.
Sure.
Yeah.
Thank you. Good morning.
This is a continuation of what Mr. Krishna Reddy asked just now. When you scale down the building size in a wind tunnel, do you also change the speed to match that? Do you actually scale up the speed of wind, or is it the normal speed?
Actually, we test at some wind speed, and we obtain aerodynamic coefficient, like pressure coefficient, drag coefficient, lift force coefficient. And after we obtain the aerodynamic coefficient, we can estimate wind load for different wind velocity.
So it is not the normal wind speed we find outside.
You know, when we scale everything down
Yeah.
into small scale, the wind speed also have to be scaled down. Okay? For example, if you make a scale ratio of model, the prototype to model is 100 to 1, the wind speed will be scaled down approximately square root of 100. It's become 10 to 1. I mean, in wind tunnel, the wind velocity of 10 meters per second, it may be equal to 100 meters per second in a real full-scale size. So we have to scale down everything.
Including the wind speed also.
Including the wind speed.
Okay,
But we will convert the result in the form that it can be used to estimate wind load for different wind speed.
Excuse me, last question.
That's
Bearing personal interest, mutual interest on the project, what do you suggest the minimum height legal limit for conducting the wind load test for the structures, tall structures?
legal limit.
For caudal limit rather.
Actually, the code
Yes. What
recommended
you-
load or pressure, they may have a limit
Yeah.
in the height according to code itself. Different code have different limits.
Yeah, yeah.
And for wind tunnel, also the one that I present, also for typical tall buildings. But if you are going to test for super tall, and the structure may become more flexible
Yes.
and may have more interaction with the wind load, then we have to change the model pattern, model type into alloelastic model.
No, my question is, what should be the general limit for the whole constructions in the country, in a country?
Oh,
Yes.
I actually give some number in the slide.
Okay.
Number say something like 150 meter.
Yeah.
But sometimes we have a client that have concern about the effect of wind load because they are nearby structure. The height is not up to 150. They already want to know the wind load for their building, which is not that tall. Okay.
Thank you.
Sir, I have one question.
Sir, if I may ask all of you to ask your questions during the recess or the break, since we're running out of time again. And we have a panel discussion in the evening. So you can just keep your questions posted and we can take them up during the panel discussion. I'm really sorry to interrupt, but we'll take forward the session.
Okay, before
Thank
we
you.
close, that is Mr. Sia,
Yeah.
who make all the slides for me. Okay, I'm just here to talk. Okay, that's all.
So, yeah. Welcome, Mr. Zia, and thank you so much for being with us online.
Okay.
So, yeah, may I request our President, Engineer Vijay K. Sanup, and our Hyderabad Chairman, Engineer Mahendra Reddy Garu, to please come and felicitate our speaker. Thank you. I need the applause again. We have a nice, beautiful weather outside. It's drizzling, and we are comfortably seated in this hall listening. So why not create a little more energy by clapping? Thank you, ladies and gentlemen. All right, now that's time for a little commercial presentation. May I invite Representative Mr. Subodh from Inventor to kindly come over. Mr. Subodh, can we have you here, please? About 5 minutes. Which do you prefer? Total 5 minutes. पूरा 5 मिनट में क्लिक कर दीजिए. That's a slide changer. आप इसको use कर सकते हैं. Just that you need to use this.
That's the next.
Yeah, that's the next. That's the back.
Good morning, everyone. My name is Sumedh from Inventa Industries Private Limited. We are basically into precast concrete buildings. So we construct precast buildings such as residential, commercial, and industrial buildings. And we also supply precast concrete elements. So since I have 5 minutes, I'll keep it brief. We'll have a small presentation. And then we want to focus on one particular project that we're doing now. So we have a small video for that. So Inventa was set up in almost 40 years back. It was basically into bulk drugs and fine chemicals. So that's been our business for the longest time, and we also diversified into button mushrooms. But specifically now, since 2016, we are into precast buildings and also into supply of precast elements. So we have an overall installed capacity of about 6 million square feet a year, and we have this through 3 different central factories of ours. We've also now set up a 4th factory, which is what we'll discuss a little bit later. All of our precast equipment is, the core equipment is from a company called Elematic, which is a Finnish company. So they are the leaders in precast equipment. So we have the core equipment from there, but the rest of it, we've done it indigenously, and we've got a lot of molds and a lot of machinery that we've made ourselves as well. Apart from that, we also have a AC block manufacturing plant. So that has a capacity of about 2,000 cubic meters per day. And also a pavers plant, which can make about 56,000 square feet of pavers. And these can be grey colored or normal finished. They can also have sandblasted, finished and colored pavers as well. So this is roughly where we have our plants. So we have 3 central plants in Hyderabad, one close to Vijayawada, and a 3rd one in Bhubaneswar. We've also now set up a 4th plant in Hyderabad for a specific project. Apart from this, we can also set up plants which are project specific. So that depends on the size and scale of a project. We can set up a plant and after the project remove it and sort of take it to the next project. So the project I want to focus on today is a project we're doing right now. It's an industrial building. It is for Hindustan Coca-Cola beverages. So this is one of the first, in fact, the first precast building, the precast factory that they're setting up. And in terms of engineering and design, it's a very complex project. It's taken a lot of our time in doing very quick engineering, design, and also logistics because of the size and scale of the project. So we have, just to show you, these are some of the elements. This is a column, a precast column. These are about 23 meters, 85 tons in weight. Some of the building pictures. This is a beam, so average beams are about from 22 to 25 meters in span, and they weigh about 136, about say from 100 to about 140 tons. And then we of course have to have special logistics for this kind of a transportation. So I'll just quickly go through these pictures so that we can show a small video for the project. And then we have other precast elements like solid pre-stressed slabs, facade walls, these gutters, and that's just an overall aerial view of the project. So I'll just request if we can play the video.
Inventa Industries Private Limited, founded by Mr. Cherukuri Satyanarayana in 1979, is a leading manufacturer of bulk drugs and button mushrooms in India. Since 2017, Inventa has ventured into the precast construction industry, taking up turnkey precast building projects and supplying precast concrete elements, including AAC blocks and precast paver blocks from their factories across Telangana, Andhra Pradesh and Odisha. With a strong belief in providing high-quality building structures on time and at the right price, Inventa Industries has recently undertaken a landmark precast building construction project for Hindustan Coca-Cola beverages in Hyderabad, Telangana. This project aims to create a modern, digitally enabled, automated and smart factory, emphasizing the use of clean energy. Spearheading the design, engineering and execution of this project, Inventa has introduced several firsts in precast building construction, including single-height precast columns of 23 meters weighing up to 85 tons per column, and precast pre-stressed beams up to a length of 25.4 meters weighing up to 136 tons per beam. They have also implemented precast 3D volumetric lift shafts with 4 lift cores weighing up to 75 tons per element, along with various other precast elements such as stair shafts, staircases, pre-stressed slabs, U-gutters and facade walls. To meet the project's requirements, Inventa established a dedicated precast facility in Medchal and deployed state-of-the-art infrastructure for handling and lifting the large precast elements. They have 2 beds for pre-stressed beams, each measuring 155 meters, and 3 beds of 155 meters each for making columns, in order to manufacture the walls and slabs for the project. Inventa utilized their second factory located in Patancheru. This facility is equipped with 5 slab beds measuring 120 meters, elematic KVT table lines, and a circulation line for wall casting. Additionally, they have 2 80-ton gantry cranes for handling at the precast factory and multiple 250-ton and 100-ton crawler cranes for erection at the construction sites. This project stands as a testament to Inventa's engineering and execution prowess, showcasing their commitment to delivering innovative and high-quality precast building solutions.
So that was our brief presentation. We have a stall outside at stall number 31, so if anybody wants to discuss something, we are available there. Thank you.
Thank you. Thank you, Mr. Subodh, for running us through the facility of Inventa. May I request the immediate past chairman of ACC Hyderabad Center, Engineer A. Kashiram, and Secretary Engineer Ramesh Karu to kindly facilitate Mr. Subodh. Thank you, gentlemen. And now we have the representative from Crux who will run us through their video. The representative is Mr. Mohammed Rafi.
Good morning, everyone. Myself, Mohammed Rafi from Crux Processing Systems Private Limited. We have a small AV for our better understanding of you.
Namaste, ladies and gentlemen. Crux Pre-Stressing Systems Private Limited is a renowned PT design and execution company established in 2005 and proudly serving the industry since 18 years, completed 1,000+ projects. Crux core strengths are well-optimized designs in terms of concrete usage, that is slab thicknesses, reinforcement usage and PT reinforcement. Effective usage of these 3 components will give the client overall economy while using PT in their buildings. Also, Crux is known for its service support and professional site working and timely completion by coordinating effectively with other contractors at site. Crux adopts, implements and follows stringent quality policies by checking each and every operation at site, also uses best quality materials and constantly improves the design and usage of PT hardware as per industry requirement. Crux executed and completed about 80 million square feet of IT space, about 30 million square feet of malls and multiplexes, about 30 million square feet in hospital and hospitality sector, about 30 million square feet in residential sector, and few more million square feet in industrial sector. Some of our projects are displayed here for better understanding. Novotel at Vijayawada, Radisson Hotel at Vijayawada, Taj Hotel at Vizag, KL University at Vijayawada Research Block, KL University at Vijayawada Skill Development Center, Trendset Mall Vijayawada, Centenary Mall Vijayawada, CMR at Eluru, Phoenix Guntur, Ashoka Golden Mall Kukatpalli, Malla Reddy Cine World LB Nagar, Sensation Bhumika Narsingi, Satyam Mall Amirpet, GSM Mall Chandanagar Hyderabad, TNR Mall Kompalli Hyderabad, One West Nanakram Guda, Mahavir Gateway Nanakram Guda, Vasavi GP Nanakram Guda, Naya Dallas High Tech City, Mayuri Tech Park at Vijayawada, Varun Beach Tower at Vizag, Namishri Trinity, Vasavi Atlantis, Green Space Marvel, W by DSR, DSR Classy, Lanco Hills Hyderabad, One Golden Mile Kokapet Hyderabad, Jain Capital Madhapur Hyderabad, Myscape AYDIV Nanakramguda Hyderabad, Jyoti Tech Park Nanakramguda Hyderabad, The District Nanakramguda Hyderabad, Sohini Tech Park Nanakramguda Hyderabad, Devika Rani Banjara Hills Hyderabad, Jyoti Granules Kondapur Hyderabad, Mantena Bangalore, Synergy Infra Hyderabad, DSR Apex Bangalore, Jyoti Valencia Banjara Hills Hyderabad, Ajara Hospital Warangal, AIG Gachibowli Hyderabad, American Oncology Nallagandla Hyderabad, KIMS Begumpet Hyderabad, Hetero Sanat Nagar Hyderabad, Toshiba Patancheru Hyderabad, Shri Srinivasa Banjara Hills Hyderabad, SVC Kondapur Hyderabad, Fortune 1, Transfer Slab for W by DSR, Transfer Slab for DSR Classy, Transfer Slab for Abhiram Touchstone at Vizag. We sincerely thank everyone associated with us throughout our journey and thank our clients for keeping trust with us, and we reassure everyone our best services always. Thank you very much for watching.
Thank you so much, Team Crux. That's a wonderful, wonderful lineup of clients that you guys have. And now may I request Advisor, ACC Hyderabad Center Engineer Rangarao Garu and our MC member Engineer Jay Prakash to kindly facilitate Mr. Mohammed Rafi on behalf Thank you. Now moving on, the next topic is very important. Of late, we've been seeing a lot of fire accidents happening in buildings, whether tall or small. But we all understand that fire can be a very, very precarious thing that can happen to any building. And having safety for fire is one of the most crucial things that we all as architects and engineers must concentrate on. Because fire can start from anywhere. Fire can start because of a short circuit, an electrical misfunction, or it can start with any other reason. And this is something which spreads very fast, and controlling it becomes very difficult. So the next topic today that we hear will be about fire design and safety of tall buildings. Presenting this topic to us will be Professor Suresh Narayana Garu. So may I request Professor Suresh Narayana on the dais, please. His expertise is in structural fire engineering. He's got 25 years of experience in the field of structural fire engineering. He's the founder director of Building Fire Research Center, accredited by NABL and recognized by Bureau of Indian Standards. He's a consulting engineer to assess the stability of bridges in Dubai for Kuwait Oil Company. He's a structural fire consultant to many companies like Kuwait Oil Company, NPCIL, BARC, BMRCL, Skoda's Germany, IC Impacts, and India Cements. He's guided 5 PhD theses in the area of structural fire engineering and has about 50 plus published journal and conference articles in reputed journals and conferences. So he has also patented one research, and he has also sanctioned almost 2 research patents to his name. So welcome, Professor Suresh Narayana. We wish to hear from you more.
Good morning. Yeah. It's a wonderful place, and we have a very nice weather outside. And let me bring the warmth inside the auditorium. Of course, before I start my presentation, I think I would like to compliment the organizers of this conference in basically Telugu only, as they say, Yandaru Mahanubavalu, Andariku na Vandanamalu. For all the organizers of this symposium. And of course, I always start my presentations with the blessings of Lord Ganesh. As you can see me also, he has blessed me more also. And now, today my talk will be on fire safety in tall buildings. I have been learning fire from past 25 years, and still I am a student in fire, because fire is a very vast subject and it is not conclusive at all. It is not conclusive at all. And now, I think, yeah. Oh, it's okay. Thank you. Thanks for that. So now, let me pray for Lord Agni to see that he will not create any problems at any corner of this world. In the, as they say, Mahajwalaya Vidmahe, Agni Devaya Dhimahi, Tano Agni Prachodayat. And let us start with this prayer to Agni. And in Hindu mythology, if we go to Hindu mythology, right, fire has been a problem from a very long time, not from today. That is, if you consider Dwapara Yoga, right, Treta Yoga, or even today in Kali Yoga. Now I have started with Treta Yoga, where Hanumanta created a lot of problems in Ravana's kingdom by what? By causing destruction with fire. I was only thinking, looking at this literature, if Ravana, when he has built such a big, wonderful palace, if he had thought of only some fire extinguishers and fire department, he could have saved his palace. And now, coming to Dwapara Yuga, every literature in Hindu mythology has taught us a lot about fire. When we look into this Dwapara Yuga, I think most of you know that there was a wax palace and the Pandavas escaped through it, which shows that if you have fire, but if you have an escape route, definitely you can be saved from fire. So this is a very good understanding from Dwapara Yuga. And now, this was in Kali Yuga. Because I am from Mysore Palace, I am from Mysore. Mysore has got a wonderful palace. As most of you, if you have seen, you can understand about it. And this was earlier built with wood. It was earlier built with wood. And again, due to fire, the whole palace was burnt. And afterwards, because it was a combustible material, they have learned that again, combustible materials has got a lot of problems, and now they have built it with masonry structure. This is the new palace. This is in Kali Yuga. And then, let me go to this most interesting thing of Kali Yuga. All of you know that in 2011, right, in September, what did happen? So, there was the biggest disaster. The structural design engineer of this building, a week before, he had an interview with the social media telling that, see, they just asked him, what's your opinion about this building? He had just said that it can take an impact of a jumbo. Just 1 week before the destruction of the building, he had said that it can take an impact of a jumbo. That is the confidence he had about that structure. But when the structure was in problem, I will tell you, the structural engineering was in tears, looking at the structure being collapsed. Anyway, a small, let me go back, if I can play, there is a video there. Okay, there is some problem with the video. Okay, anyway, most of you have seen that. Let me skip that. So now, I am going to start with some basics of fire, because basic will be the same, whether it is a tall building or whether it is a short building or whatever it is. Get this sound? So this is the destruction of WTC. Of course, people thought that, most of them, they had still that confusion that whether it was because of the impact of the jumbo or it is because of the fire. But one thing we have to understand is that all the aircrafts, before it takes off, it is filled with complete fuel. And when the plane came and struck that building, it was not just the impact, but it also contained fuel in it. So, because of the fuel it contained, right, it caught fire. And the WTC being a steel structure, you know that, right? The steel lost its ductility, and there was the collapse of the structure that has taken place. So this is a very solid example for a tall building, collapse of a tall building due to fire. So now, I want to just put it in a very simple way. What is a fire? Fire is nothing but a combination of unstable gas plus oxygen, which will give you, right, stable gas, heat plus light. Let me not go too much into that. So now, this is called as a fire triangle. See, fire triangle or love triangle, both are problems. So you know that? So fire, if a fire has to happen, three important things are very much essential. One is fuel, the other one is oxygen, the other one is heat. Any one of them missing also, you can control the fire. So this is called as the fire triangle. So any one of them missing also, this can be controlled. So next, we would try to understand what is heat versus temperature. Heat is basically a transfer of energy from one form to another. Temperature is basically a measurement of how hot or cool it is. More scientifically, it will be a measure of energy of the molecules of a substance. So I also don't like to go too much into the science of it, but let us understand this, the difference, right? So whatever may be the heat, the temperature may differ, right? The same heat of 3A may produce the same temperature of 1A. Anyway, this is what... now, forgetting that, let us not talk too much about that. This is very important as a structural engineer or a fire engineer. The behavior of fire. This is the fire dynamics. We call it as fire dynamics. So basically what it happens is in the fire, right? First, the ignition takes place, and you can see that there is a curve of time versus temperature here. So in the time versus temperature, you can see that slowly the ignition starts. After the ignition, there will be the growth. But the most interesting point here you have to observe is, in between the ignition and the growth, there is one point called as flashover. The flashover is a very, very important point, right? Because at this point, what happens means, basically after the ignition, slowly all the items around starts burning, and then the temperature rises to the ceiling of the building, and because of the heat in the roof, so what happens? The heat will be reflected upon all the articles in the building, and everything starts burning. And this is the most dangerous time. So why I am trying to tell you this is, anything has to happen, it has to happen before flashover, any escape, any prevention, any protection. Once it starts getting into flashover, right, you cannot save any lives also. It's very, very tough. So this is, normally this will be the behavior of the fire. So it will be ignition, right, flashover, next it grows, then the decay will be there. Now, this is just an experiment which has been conducted, right, in US, right, to know the behavior of fire. I think, can you help me again? There's a video here. Yeah. So this is what I wanted to show you. This has been an experiment conducted to know the behavior of fire. Whether it is a short building or a tall building, the behavior will be the same. You can see this, right? The ignition has started there, and slowly you can see that the flaming molten falling all around, and the sofas getting caught with the fire. You can just see this. You can observe this. And this gives you a very clear idea of how actually the fire behaves. Before we do anything, we have to understand the behavior of the fire. So slowly it is trying to spread itself. You can, as I have told you rightly, it has gone to the ceiling of the building. You can just see that. It is going, smoke is also increasing. Smoke is one of the side effects of the fire. You can just see that. As the heat increases on the surface, right, it reflects the heat on all the items that are there on the, at the floor level, and that is the time where the flashover takes place. The whole thing burns. You can just see this. So, as a structural engineer, we have to see that whether my structure will be safe between these two periods. That is, between ignition and flashover. So, now, of course, this is what I had just shown you. This is the fire initiated, and you can see that the fire grows, and then fire spreads to the nearby surfaces, and hot gases rise up, and of course, hot gases accumulate and spread at the ceiling, and you can see that it reaches a point of flashover. All the material burns, and that's it done. So now, see here, some of the key points we have to understand about the fire dynamics is the fire spread depends on the material and ventilation. It depends upon the material and ventilation. And lighter objects catch fire faster, and they burn faster also. And places with lot of ventilation, people think that if there is lot of ventilation, no. It helps, of course, for the fire to spread. And arrangement of the objects inside a building also definitely makes this thing. And fire moves towards windows. So just one more this thing I would just like to show you here. More the ventilation, faster will be the growth. Again, this is one more video to show you that they have conducted an experiment, right, to show that more the ventilation, the fire grows more. You can just see this. Of course, also they have organized the objects at different places, and then they have tried to see what happens exactly, right, how the fire behaves in these conditions. In just would you like to see this? Shall I go to the next slide? I want a few of you to talk to me, no problem. I'm not in a classroom. Would you like to see this, or shall we continue? Huh? Okay, thank you. So these are some of the experiments that are being conducted, and of course, fire behavior is also very bad, and fire experiments are also very expensive. It's very, very expensive. Because people say that you all make money by construction, but I make money by destruction. So I burn something and I make money. Okay, so that is what it is. Yeah, I know. Not by burning, for protection. Let me say that. Okay. Yeah, you can just see this. So these are all some of the experiments that are being conducted, because basically in US and other places, they give a lot of importance to what? Fire. Because they care for lives. Here I don't know what to say, right? They care more for lives. And you can just see this, yes? Just to show you, right, if there is more ventilation, right, how the fire will be. Okay? We'll go to the next one. So now, in fact, we have started working in a small way, right, about the collapse load mechanism of tall structures due to fire. This is a small finite element model we have done, right? And now what we have done here is, in certain ways, we have tried to induce fires. That is, we have tried to induce some short fire, long cool fire, and standard fire. All these fires have been done, not simultaneously, uniformly, one after the other, to study what will happen to the structure, right, when these fires are being ignited, or when these type of fires, right, like ISO fires, long fires, and short fires. And I am going very brief on this. You can see that we have done it at the corner bay, edge bay, we have called it, and we have taken some 4 different cases here. And this is one more interesting case we are studying, that is the traveling fire scenario, right? When the fire travels from one end to other end, what exactly happens to the structure. Now, some of the conclusions, what we have got is, the fire basically affects the columns because it undergoes significant expansion followed by large deflections, and the critical scenario is the edge bay 9 meter by 6 meter. That means, why this plays an important role means, before the construction, if I can make an analysis, right, then I can really think as to what kind of protection I can give in case of an eventual fire, to see that there will be no total collapse of the structure, right? So that is the reason we are trying to work on this, and this has been published in Elsevier also. And of course, we have seen that these columns undergo significant expansion, and then basically column starts buckling at 600 degrees centigrade. This is a steel frame. So it started buckling at 600 degrees centigrade. So the critical scenario is the edge columns. Edge bay is the critical problem. So now, by knowing this, right, if I know beforehand, before I design, right, what is the kind of protection I can give to that critical columns for fire can also be thought of. So the basic objective of fire is to see that there will be, point number 1, objective is, first one is to save the firefighters. Object number 1 is to save the firefighters, because if they are gone means nothing is this thing. Number 2 is life safety of the people. Number 3 is to see that the structure will not collapse at any event of fire. So these are some of the small work one of my PhD student is working upon. Next, of course, I told you that even in the traveling fire scenario also, we have observed that it is driven by the internal exposure of the columns when the fire travels from one phase to another phase. After knowing something about this, of course, this I don't want to talk because most of people I would have told you about the classification of tall buildings. Now, we will go to the factors which are going to affect in high-rise buildings. One is management factor, the other one is human factor, the third one is technical factor. These 3 factors play a very, very important role. Of course, Dr. Venkatesh Kodur is my good friend, right? He has presented this in one of his papers. Of course, what is very, very important here is the exit path, protection system, type of occupancy, whether it is hospital, whether it is a residential building, that has to be taken care of. And then the fire design, I'll be talking about a little about that further. And regulation enforcement, how much of enforcement has been done. And then technology and firefighting resources, what you have. And then common civic sense. These things play essentially an important role in case of fire safety design in tall buildings. Of course, the same thing we have discussed much here. Now, this is to show you again a video of a hotel in Mumbai. Recently, why I wanted to show you this is, you can see that this has happened in the top floors or the upper floors. The problem was not just bringing in the fire engines there, because you know the traffic of Mumbai, by the time they come, it will take a lot of time, and also whether they have the sufficient equipment to reach that point, height. So that was one more bigger problem here. So, and you can see that we are being saved here in India because the time for burning, right, or the time for the collapse of structure is taking a longer duration because the material we are using here is concrete. If the same thing has happened in US or other places where they use more combustible materials, right, the situation would have been totally different. So only God save us. Next, these are some of the notable fires in tall buildings. Of course, the latest was in January in India, in Mumbai. Of course, 6 people died and 23 members injured in this fire. This was one of the latest tragedies happened in January 6, 2022. Other details are given here. Now, what does our regulatory guidelines say? What does our regulatory guidelines say? Basically, the NBC code, right, speaks on 3 important features. What are those 3 important features? Number 1 is fire prevention. So first of all, always prevention is better than cure. So to prevent it, and next is fire protection. The next one is the life safety. So looking at all these things, fire prevention, fire protection, and life safety, all our code has been, all the guidelines have been formed. Basically, these are the 3 features on which we are working upon. Now, so let us look what are the guidelines we have with regard to fire prevention. So in fire prevention itself, they have classified the buildings into hazardous buildings, medium hazardous buildings, and then high hazardous buildings, and also they have given what should be the type of construction in table 1. This is the general guidelines for all buildings. Hazardous means low hazardous, medium hazardous, because low hazardous will be our residential houses. Medium can be anything from your petrol bunks or whatever it is. And then high hazardous will be highly inflammable places. I'm going to show you a few examples of how high inflammable these things causes fires. And this is the one, let me go back. This is the one I was telling you about, the table 1, which speaks about the sizes for the walls also. I don't know how many of us really follow this, right? While doing designs, we'll be more concentrated. Yeah? I don't know, I said. If you are all following it, fine. I will thank you for protecting a lot of people. Right. So these are the guidelines which are given basically for the protection. And basically here you see, I want to tell you about this cover factor. This is given in, if I remember, IS 456, table 16A, right? There he speaks about the duration, right? If I give you some 20 mm cover, 3 hours, 4 hours, what is that for? What is that for? Means because it gives sufficient time for the people to escape so that the building will not start collapsing and they should not become panic about it. That is why, but I see that you sit in the office and you give all the cover, details, everything, but on the site, they keep a small jelly and they will say the cover is over. So this is the problem, because they don't know the importance of the cover. Most of them, they don't care about the cover. So actually, the cover plays a very major role in fire protection also. Not only in corrosion. People think that it just causes, it gives protection towards corrosion. It's not just towards corrosion. It also gives this thing towards fire protection also. As you have all seen, it is the time between the ignition and flashover. That is the time we have. We have to see that, right, nothing collapses during that time. Right? And we have got, within that time, the fire protection group should come to the site. Otherwise, everything will be gone. You'll hardly able to save anything. And you have to see that if there is any opening filled, should be filled with good fire stop material. I'm going to show you a nice video here, how the fire spreads in a hospital, because they have not filled it with stop firing material. So, and then exits and passages. This is one thing. They will show fire exit and everything, but when I go there and see some of these audits, when I have done some fire audits, I see that it will be a go down. Nobody can go out of that exit at all. So these are some of the common problems. And then signages. Signages are very important, and fire command center should be there. Now, of course, for fire protection, coming to the fire protection regulations, type of installation, pump capacity, I don't know who does the design for this. If it has to be actually be designed for the pump capacity, and in some of the apartments, let me be honest, they have shown the same sump for fire as well as for regular water supply also. And when there is a fire, I have seen actually when the fire engines come there, all the water would have been used, right? There will be no sufficient water supply, because of which they have not been able to extinguish the fire also. So please do take care about it, especially in tall buildings. Because as I have told you, these fire extinguisher people only will have some basic problems of reaching the top, and added to that, if they don't get sufficient water, which is going to create a lot of problems. Now, and then you have to see that, see, now when I came here, I saw only 2 extinguishers here. Huh? I don't know why. So, we don't know how safe we are here. Let me pray God nothing to happen. Anyway, just I'm telling you. So, now, you see how it has to be placed. So, we have to use the right type of extinguishers throughout our exit way, right? I don't think there is a single extinguisher throughout our exit. So, I'm just telling you. So, we do talk about it, but how much we are practically doing it is more important. Because we have got this attitude, chalta hai attitude. Okay, when fire happens, let us see. Right? When it happens in some buildings, then we will talk big about it. Fire protection, fire safety, fire regulations, and all these things. But before that, how much we do is very, very important. Where to place it means along the escape route it has to be placed. Now, of course, even the exit capacity should be calculated. The exit capacity should be calculated depending upon the occupancy load. Right? If there are 1,000 people or 100 people, depending upon the type of the building, whether it is residential, whether it is hospital, whether it is a convention center, based on that, and then compartmentization is very, very important, so that the fire does not spread easily to other places. Compartmentalization is very, very important, and fire drill and these things. So this is coming to fire protection, if I want to protect. Then coming to the life safety, right? The fire has started now. I have not been able to protect. Then what is the next thing? Next thing we have to look into is whether the exits have been designed properly for the escape, right? So exit should be, as I said, that it should be free from obstructions, and then the maximum travel distance has been given in this table 5. I don't want to go through that. You can see that in NBC. Next is how to calculate, right, the width, etc. has also been specified in the NBC for the exit, right, for a given place, whether it is a residential place or whether it is a this thing, educational, institutional. You see, I don't know how many of you remember that Kumbakonam tragedy school in Tamil Nadu. It was a very major fire accident where most of the children were burnt alive on the top of the building because it was a horrible fire accident. So now, you see, these are very important things. And then occupancy load is also very, very important. So based on the occupancy load, floor area, the number of people, right, the things, exit can be decided. These designs are available. And then compartmentization. How much should be the compartmentization? If I want to really avoid the fire, and it should be done by fire-resistant walls and doors, fire-resistant doors. And fire officer drills are must, and it is mandatory. These are all coming under life safety. Why I am telling you life safety means, if you are not able to protect, the next thing is to look for the life safety. And then fire officers and drills once in 3 months. This, all of you know that. I just don't want to go there. And then, you see, just because I follow the code, don't think that I am safe. Because you just see here, there's a small video again here, please. Can you help me out? Oh, just go back, sir. Just go back. Oh, no, no, no. Sir, where are you? No, go back. Back. Still? Where did you go? Ah, yeah, here. Yeah. Just because you follow the code, it doesn't mean that you are safe, but you have to keep your premises perfect. Just see here what's happening, and it can create a problem. So, next one, we'll go to the next. This is with regard to that Lebanon, right? So whenever we design a structure, it should be known for what purpose it is designed, right? Blindly we cannot, in fact, there is a subject by itself called as blast resistant structures. If I am going to put in some ammonium nitrate, right, then I should design it for ammonium nitrate, right? I can't blindly put anything anywhere. This is a small example of that. So let me play this video for you. The first one. He has gone to the second one. Okay. Yeah, first one, please. You can see this. This was the one that what happened in Lebanon. You can see the explosion. You can see. So whatever reinforcement, whatever concrete you have used, fire makes it into pieces. So you should be extraordinarily careful with fire. And fire is, one good thing about it is, it has no discrimination. It can enter into Biden's house, it can enter into Modi's house, and it can enter slum also. And it can come into my house also. So why I'm trying to tell you is, fire is unpredictable, most unpredictable. Next one, please. Yeah, just, you can see the amount of smoke. You can see the destruction it has caused. Now, this is what I was trying to tell you. This is, you should put proper fire stop sealants. Otherwise, how it affects. You can just see this video. In a hospital, what has happened? You can just see this. Can you please? You see that? A small sealant was not taken care of, and a fire starts from there, from the ducts, and it is carried throughout the hospital. So, see, this is also all a high-rise building only, high-rise hospitals only, right? You see what has happened? So small care, if you don't take even the fire alarms, nothing can do anything, because it has started slowly and it has gone throughout the structure. So, this is the thing. So, how the fire spreads very fast. So, that's why I said that, right? This is in Ahmedabad. It was a COVID hospital. It caught fire, right? And 5 women and 3 of them, 5 men and 3 women, right? They died not because of COVID, because of fire. See the most unfortunate thing, right? So this is happened again at the top floor. And then flammable liquids, it should always be taken care of. See, if I don't take care of flammable liquids, can you put the second video, please? You can just see this. Again, this is on the top of the tall building. What has happened? Flammable liquid. You just see this. So how critical it becomes. Can I take few minutes? I got some 2-3 interesting videos. Okay, go to the next one. Move to the next one, please. So, let me not take, this is one thing. Housekeeping is very, very important. I want to just play this video. You just see this. This is very interesting. On the sites, people working on the sites especially should see this. You just see, this is the carelessness of the people working on the site. You can just see this. So this is only poor housekeeping. That is why even at the sites, you should be very, very careful. Yeah, this is the incident that happened in Bangalore, right? Carlton Towers. You see, because there was no proper, in fact, this is a video. Just 1 second, you can show this, right? You see, next one, previous one. Okay, because they did not have proper escape, right? They had to pull the people through ropes. Now, they are coming out with new techniques for escape routes. This is very interesting. Yeah. For evacuation, these are some of the new. now they are coming out with these chutes, right, to bring down the people in case of. So this is one of the new developments that are taking place. Yeah, next one please, the last one. See, this is one more thing that is being followed in China now. This will open up in case of an emergency, these stairs, and people can come down. This is the recent one. So, with this, I would like to end my presentation. Thank you. I have given you a brief eye-opener. I think I have been working for 20, 25 years on fire with, as a student still I am working. And this presentation actually I had to prepare a bit more than my PhD viva also, because Rajkumar was very particular about this. So I came with my butterflies in the stomach. I hope I have done some justice. Thank you very much.
Thank you, Dr. Suresh Narayana. I think that was one session everybody enjoyed. It was quite informative. And as you say, you know, fire which can be lighted for cooking food or providing light can also be hazardous, and it can be very, very perilous for human life. So thank you so much, sir, for that wonderful, wonderful presentation. May I request our MC members, Engineer Jaiprakash and Engineer Bhanu Prasad, to please come over for the felicitation. Any
Hello,
question
sir.
and answers? I know
Yes,
there are
sir.
quite a
One
few
question
question
is there,
and
sir.
answers. One
Sir.
minute.
Yeah, sir, here, sir. Sir, very nice presentation, sir. I have two questions to answer. Here, sir, here.
Right.
Yeah.
Yeah. Yes,
Very nice presentation, sir. This is Dr. Narasimha. I have two questions, sir. The modern TMT bars, most of the manufacturers are saying that they were rated up to 6 hours of fire rating when compared to conventional HYSD steel. Is it true? Or do you have any findings on that?
Sir, as of now, I don't have any proof to tell you about that. So it has to be 6 hours means under which curve, how it has been tested, all this documentation has to be seen, and then only it can be certified. And it has to be tested for that, really.
My second question is, sir, regarding the apartments planning for the 6 stories and so,
Okay.
we are using only the main entrance for both the exit and the entrance purpose.
Yeah.
In the event of any fire is there, the escape in most of the apartments is through that entrance only. Okay. Do you have any suggestions other than the staircase?
No,
what you have
no, emergency exit. Staircase is the only, now, as of now, emergency exit, right? Because there is no other way, because you can't come through your elevators and escalators once there is a fire, right? Because if there is some problem with the power and everything, people will be gone. So as of now, it is only the staircases, and you have to provide them with sufficient, proper staircases. And I said that the exit should be very clear. The passage should also be clear without obstacles.
Thank you, sir.
Sir,
nowadays,
I would not be taking any questions, sir. Please kindly connect with Dr. Suresh Narayana. He's around in the hall, and let's take it up with him one-on-one. Thank you so much for saving the time. And Bhanu Prasad and Jaiprakash, please come over for the felicitation. Yeah, So after these two wonderful sessions, now we proceed for a tea break, which will be just for 10 minutes. And we missed one most important speaker yesterday who could not make it yesterday, but here he is today amongst us, Master Strobala, and we are all looking forward to listening from you, sir. So let's all go break for tea and come back within 10 minutes. 10 minutes is 10 minutes.
ಸೈಡ್ನಾಗಿಂದ ತಾಳ್ರಿ ಕವರ್ ಆಗಂಗೆ.
Okay, time for us to get back to the room. Please settle down. Our next topic would be high-rise complex geometrical facades and how to maintain high complex geometric elevations, and this would be presented to us by Mr. Mahesh Arumugam. So may I request Mr. Mahesh Arumugam to please come onto the dais. We'll start the presentation. Mr. Mahesh provides the strategic leadership as the director for Manhat's India Facade Consultancy business. He's been in the facade industry for over 22 years, and his experience ranges from aluminum glazing systems to precast concrete facades, BIPV, BILED enhanced systems, and stone cladding. As we all know, whatever be the building inside, but the envelope of the building or the facade of the building is the most important factor which draws us to have a look at it. The facade is the most impressive part of the building, and we first try to appreciate the facades more than the interiors because that is the first touch point for us. So may we listen to Mr. Mahesh Arumugam on this particular topic. Over to you, Mr. Mahesh.
Okay.
40 minutes, and maybe 5 minutes for Q&A. If it is 45, I will not take Q&A.
Sure.
Whatever you want.
I think good afternoon to all. I think we've all refreshed back, and we're going to have a refreshed subject on tall rise. Is not working? Okay. Okay, just getting into it. Just press this one. The presentation outline is what is a complex facade in a tall rise, high rise, what do you call? Designing a complex facade is a challenge, is a complex chemical and civil and structural and mechanical engineering, and issues faced by the designers when it comes to complex. And a few case studies I put up here on projects in India, the most vulnerable and challenged complex geometries. And how to maintain, even if you create a complex geometry, you are unable to reach, and you need to how to maintain the complex geometries. And then what are the projects we've done in Hyderabad, which I present some of the case studies in Hyderabad, which are the structural marvel wonders, hidden marvel wonders in Hyderabad. You may be not aware of it, but is an icon project of India in Hyderabad. The complex geometry should be thought process, think out of the box, and it has to be designed such a way. You see, we have a big problem in India. All the cities do not have a proper urban infrastructure when it comes to high rises. The skylines of the, I think, look at the high-rise building in Asia between last 15 to 20 years. Singapore skyline evolved in 1985, started, and is full swing in 91, and 97 crisis is slowed down, and 20 it picked up. And today you can see what is Singapore skyline, which is a proper urban infrastructure where we can build the tall high-rises, where it does be assigned some places like Robinson Road or Orchard Road. In India, such a structure is, urban infrastructure is not there. Same thing in Hong Kong skyline, which is started in 1980s, and today the ICC tower done by us, and it is today stands still as a urban infrastructure, tall high-rise buildings. Coming to Dubai skyline, it started in 2004, and today is evolved very aggressively and very fast track. And you know what is the iconic structure and complex geometries in Dubai. And coming to Kuala Lumpur building skyline, it also started in 90, but a slow economic process is slowing down and moving forward. Across our sea neighbor, Colombo, it was a situation in 2009, after war. It was 2014, and their vision in 2021, this was a vision. Unfortunately, economical crisis, they stuck and unable to move forward. And that's a vision for them. And I think it will move forward because it's slowly picking up the economy. Coming to Bangalore, you see what is the skyline, because we do not have a proper Robinson's Road or Sheikh Saidi Road, or in Hong Kong, Wanchai or Kowloon, no such a infrastructure, urban infrastructure road in India. So we have big challenge and trouble for the next 20 years, how to develop Dubai skyline or Singapore skyline or other international skylines. Same thing in Mumbai, at least evolving, but still we have a lot of slum issues and is coming over the skylines in tall rises. The main tall rises, you need a proper urban infrastructure, like earlier our presenters presented on wind, fire and other access, which is key for tall high rises for urban infrastructure with full facilities. Chennai, you look at there. And same thing in Delhi, NCR is coming up. Most of them are residential high rises and not commercial high rises. It's spots and pockets. So it's not a fully developed urban infrastructure high rise skylines. Same thing in Hyderabad and same thing in Calcutta. So look at this temple. How many years old this temple? Why I'm presenting this temple? It has whatever technology evolved today, it has been implemented in 1,000 years ago. And this is the Tanjore Pragadiswara temple, and it started in 1002 AD and completed in 8 years. Even here we are struggling with the sky rise in India today for 10 years, especially Mumbai and other areas. And these are such a art, and each are completely granite structure. They built in 8 years in that 1,000 years ago. And it has an identity, sense of identity, where today the infrastructure, master infrastructure, entire temple is not flooded on today in 1,000 years. and is a self-shading tower, only in the world, and today is the tallest high-standing complete granite structure in the world. And it has a complete roof thermal transfer values, it has complete envelope thermal transfer values, it has also over thermal transfer values, where it is today stands still for the global UNESCO heritage. Here the waters are drained and it not come to there. It has a perimeter drainage which go into the Kaveri sub-canals. And today it occupy for Shivaratri, Bharatanatyam functions, it can occupy 10,000 people after 1,000 years. This is what we call urban infrastructure required in India, and it for any high rise. This building is at 216 feet high and the tallest granite stones, and not a problem. I didn't know that 1,000 years ago how they identify the granite as igneous rocks or sedimentary rocks or metamorphic rocks, how they tested the stone, and it's a completely Flemish bond with the art integrated into the Flemish bond, and it stands still. This is what India, and today we are Indians, we are suffering on urban infrastructure and high-rise towers. So, as I said, is architecture, design to engineering is and it has to consider the environment which all impacted 1,000 years in India, and still we are struggling today. So we need to have the sense of identity in India. Coming to the subject, the theory of curtain wall. See, look at this, what the human skeleton, which has all the junctions, whatever engineers design, like pin joint, fixed joints, slot joints, everything, body is flexible to accommodate. Same thing whenever you do high rises, it has to be flexible for building sway, live load deflection, and integrating into everything. So this is your complete MEP, mechanical, electrical, plumbing, all functional aspects, which has to integrate into the tower, into the skeleton, which is naturally adapted. And same thing has to be energy performance and environmentally you have to survive. Otherwise, your life is gone. Same thing. What we are talking about internal coefficient pressure, what are you talking about external coefficient pressure, same thing what you are addressing on the human comfort. And your body has internal temperature and your external temperature, you are cooling the building. In Europe, they're heating the buildings. So it has to be addressed with all envelope thermal transfer values, with the temperature coefficients, with the internal, external, as well as roof, whatever you are getting in the tropical environment where we are living. So it has to be a heat balanced body. So the same way you are building, whatever you are building for high rises, it has to be a heat balanced tower and environmental friendly and occupants comfort. So where we are providing, because we are in tropical environment, we have this attire, and we cannot have the attire around the years like this in India. So we have to also design the building on local environment consideration and local built suit conditions as well as local requirements. So because the Europe, they have a heating the building, so they require such attire for move around and environmentally functional around. So we must understand whatever we design, we should design according to our tropical climates and tropical environment and tropical situations. Look at this. Today the complex geometries are evolving, such things like this ant's nest, which is built in Netherlands, and same thing, bird's nest, which is built in Beijing. So this is a complex evolvement of today's building design in coming towards the next century. See, these birds are designed to survive themselves, which they are in hanging on the air, they swing in the wind, all wind dynamics, everything they are struggling and suffering and living. Where they are traditional green straw, dry straw during winter and green straw during summer, and in deserts they have the roof thermal transfer value nest. So these are the design principles they are doing themselves. Why we are not adopting? Why we sacrificing? Why we materialistic? Why we are diversifying ourselves to cost-cutting measures and vulnerable ourselves? This is a key in your tall rise buildings. The design principles. See, building facade does not carry any dead load from the building other than its own weight, because facade is a secondary element and non-load bearing element. So you can complex it and you can shape it and you can fix and install. Loads are transferred to the main buildings and the structure through connections to the floors or columns or beams or slabs, it can be connected. And the design to resist air tightness, water tightness, as well as wind forces, as well as seismic forces, as well as its own dead load forces, where it has to be tested for proof load. Also, we tested for any cantilever element, it has to be withstand its load impact, otherwise is failure. Also, we test for any building more than 50-meter height, it has to be bonded with the lightning arrestor. Many high rises where the fire happening on raining season also because the facade are not bonded above 50 meter with the lightning arrestor. Knowingly or unknowingly get fire, sometimes because of lightning strikes on the facade because metal exposed to the building envelopes. Also, any one available facade system, there are different facade systems in the industry which can be accommodated and adopted, but not at all in every design. So, as I said, the key design factors in the facade, you need structural, because facade interact with the structure. Many people believe that you just hang the facade between slab to slab or beam to beam or column to column. If the job is over, is not correct. It is highly vulnerable, is a failure because you are spending the highest amount of money in the project. Total estimate is in facade, either in facade or in foundation. Sometimes foundation get into 10 to 15%, or sometimes facade get into 10-15%. So we have to be very careful when you're designing and installing facades in a high rises. It has to be addressed with the structural in terms of live load deflection and building sway, and also it has to address with the electrical by bonding for all the parameters of electrical means. As I said, the lightning strikes, plumbing, you need to drain the facade in pressure equalization and vent path, otherwise water leak will come into the building and you are unable to address at all for the lifespan of the building. Also cooling inside the building, so it has to be designed with, many people just do the heat load calculation based on the HVAC, which is not the 100% give the comfort of the building envelopes. For example, you stay, people in many IT parks, we are now doing rectification remedial because people ask for a seat change. Because they sit near the glazing of 1 meter, they say radiated heat, direct heat, uncomfort, they are unable to sit. So people ask for a seat change. So you got to be carefully design the facade for cooling and comfort environment, occupants comfort. And also heating. This is what I said, radiated heat, direct heat, your air condition is not balanced. So it again is a problem in the interacting with the facade. So it's a blame game between HVAC, facade and other elements. It happened in the project. As for aesthetics is a key. Whatever you complex design, it has to be aesthetically done with all engineering things. Also weatherproofing, as I said, air, watertight and completely test for 33 to 40% of the design wind pressure is better. But here they take the minimum code value for testing for 300 Pascal, which is not advisable. We are in a tropical environment, where 3 months we are continuous monsoon. Coming to acoustics is a very large and vast subject. Your airborne acoustics, your vehicle acoustics, even sometimes wind funneling between the two buildings if a close proximity, you have wind funneling effect of acoustics. Acoustics is a vast subject. It has to be site tested and readed for the peak and non-peak hours and tested and design the acoustics for the building envelopes accordingly. Coming to buildability is a very key, is the most vulnerable element because Professor put a very nice wind tunnel test report on positive pressures and how negative pressure behaves. And any facade element you have to do, the maximum pressure comes under negative pressure. So the building facade has to be designed under negative pressure when come to buildability and durability point of view. And other project specific requirements, whatever projections are recessed or inclined or outward, so it has to be carefully designed. The wall properties of the facade is you have to address with the control of heat flow in and out, and as well as you would address with the airflow, and also you address the water vapor flow. You know, sometimes the surface or kinetic energy, the wet moisture sticky to any absorbing material, you have to be carefully address the control water vapor flow. and also control rain penetrations. This is very key. Otherwise, because the fabrication facade is, the tolerance in millimeters. Your structure has a 25 mm, 30 mm tolerance, but when it comes to facade, the tolerance is 1 millimeter for thermal expansion, 1.5 millimeter for fabrication, and 1.5 millimeter of insulation. So where you fail, you get a water penetration leak. In a building, you are unable to arrest the water tightness. Especially the residential project, you have to be careful. In commercial, we can get along with at least fine mitigations and things. But residential is very not easy to rectify because you have 500 tenants, you have 500 windows repairing is a not easy task, which Singapore addressed in 97, window falling and everything. And the Singapore government does you know what to do. They form a committee, and that committee from globally facade experts, and they discussed and they decided government will pay 50% and owner has to pay 50% all window falling. And from that effect, by law, 2000, everything will be rectified, building built before 2000 will be rectified under this government scheme by law. After that, only the owners and the contractors are responsible for handing over the facade for prevent window falling. After that, the contractor is responsible. So this is the situation happened in Singapore, and they may overcome. It took 5 years to overcome. So the window and openings, light, solar, radiation, other things also need to be addressed in design. Also the noise, as I said, acoustics, and also fire. Very good presentation by Dr. Surya on the fire. It was a fantastic presentation, but he not touched upon the passive fire protection when coming to cavity barrier in between the facade and interface with other trades, which is a non-load bearing element, which has to be a 2 or 5 rating, maximum in the table, whatever is shown. Many of the buildings in here, the fire cavity barrier horizontally or vertically not addressed. And also we have leaf frog effect and chimney frog effect in the fire, where it has to be addressed with either sprinklers with the fire stop and smoke seal, or you provide a vertical separation of 900 mm without sprinklers. So this is not happening in India. That's why we've seen a lot of fire accidents in Mumbai, whatever, so people dying. So we have to be careful in controlling the fire when it comes to leaf frog effect or chimney frog effect outside of the building. And also provide strength and rigidity to facade, because cleaning time impact and gondola, all this, it has to be designed for live load, human live load and impact loads, and it has to be durable and aesthetically pleasing as per our architectural design, vision and view of the buildings, and be economical because you need to source the local material, otherwise it's a very expensive affair when you're doing the facade. See, as they mentioned the typical wind flow patterns, I don't need to touch too much, but the wind velocities between the small tower and the big tower is maybe twice that, sometime free wind or cut wind or east wind. So you have to be carefully designed, otherwise the corner condition is vulnerable in the facade elements which may get damaged or fall down. So you have to be careful. And also how the maximum wetting portion, this is a wetting map of any high rises, which has a generalized pattern of wetting on a windward direction or outward direction or facing the elevation in a multi-story building. Even it's a rectangular building, this is a condition. If any geometries other than rectangular or square is completely different wetting pattern. So we have to be carefully address the drain, channel, vent path, and the pressure equalization in the facade. And also if rain continues for a long period, water will bring down to the center of the building, where people are sometimes designed on the economically to 25% center zone. You can optimize the wind pressure as per code standardization, which is, again, you have to be careful, which is vulnerable for wetting and water and drain leakage at the center of the facade. The types of facade system currently used in India is our stick system, which is a traditional system which is used for shop fronts. And because the 3 is everything knocked down at the type and install. Coming to semi-unitized system is partially glazed in the factory and partially installed at site. And high rises in ribbon type window system, where you have only continuous ribbon type, then you can use a ribbon type. And this unitized system is globally adopted for high rises. which can 100% fabricated in the factory as a full panel and come and hook on with the locked. And we would be very careful when installing the facade, unitized facade on high rises. You have to be locked one side and one side to allow for movement because the building sway and everything, as well as the seismic point of view. Otherwise, the seismic comes, the panel bent and glass break and is fall down. So carefully, you have to one side locked and one side free to allow the panel movements. The structural performance must withstand the wind forces on it. As I said earlier, it's a non-load bearing element. It has to withstand applied forces, so especially on the dead load, wind load and live load of the facade elements, not any other loads. And coming to must ensure occupant and passerby safely. Many people understand tempered glass is a safety barrier. Glass is not that. It only safely break. When you have a safety barrier, you need to have a laminated glass or provide any railing or anything as a safety barrier. Otherwise, even tempered glass breaks, it shatter, and the safety is not there. Also must appear visually safe. Otherwise, because the internal coefficient pressure, you open the door, the other window vibrate. So you have to limit the deflection. You have to limit the deflection of the entire systems to keep the comfort level. Otherwise, somebody sitting in the chair at the cabin and suddenly some staff come and open the door and the door closes with the door closer. The window rattles. So which is vulnerable and uncomfort. So it has to be limit the deflection in all elements in the facade because facade is complex with the chemical engineering by structural sealant, weather sealant, gaskets, address with the hooks and pin joints and cleats, many components. It's got a nearly 25 components integrated into as a one facade element, which is applied to all engineering, chemical engineering, you name it, chemical, mechanical and structural engineering. And also based on the computation and data sheets, we have to be very careful limiting the deflections and other values and accommodate the building movements. You have to be very careful, you have to accommodate all the building movements. Otherwise, the glass will start to break. You don't know what the reason is, glass is breaking. So movements is a key, and you need to have tolerance is also key when you design and install a facade element. And define the horizontal and vertical modulations. So it will help the glass wastage, minimize the wastage, economical options, many things to address. Also, window to wall ratio, you can do this with the 30 to 40 to 60% or 50 to 50% or whatever you design derives. And also the glass thickness to be optimized, so it will be economical. So otherwise the glass, if you under design the glass will shatter periodically, then you are forced to replace all the glasses. Also especially the hardware. People are just putting one single lock. In very high negative pressure, the lock will gone and the window will open and fall down. So you have to be careful whether 2-point lock or 4-point lock or a 6-point lock based on the aspect ratio of the window as well as the negative pressure wind conditions. And you have to test the window and for open condition and closed condition, then only the window stays and sustain for the lifespan of the building. So these are the structural performance, as I said, the live load deflection, building sway, the shortening of the columns, the over deflection of the slab. These all need to be limited in structural design. It has to be coordinated. First, facade design has to be coordinated with the structural slab deflection. Otherwise, you end up with the aluminum mass will increase like a big walling, and you end up with paying more. So optimization of the structural slab design, the deflection to be limited between should not exceed more than 20 mm. Most of the cases go on beyond, but it has to be suggested for best value engineering. I don't call value engineering. I hate value engineering people speak in India. I call it as engineering value. So you have to limit the slabs to 12 to 15 mm to achieve better performance of optimization of material and everything. The same thing, what all the structural engineers discuss. So we have the building sway. So you have to address for the between panel to panel movement. Live load deflection also you need to address. Then any sloped facades inward outward, then you need to laminate the glass because the loads are not transfer 90 degree inwards. So you have to be careful. Also is a safety concerns. There are codes and calculations. I think this is how I shared these presentations. You can see in all the points what are the limiting deflection, thermal movements, fabricate tolerance, insulation tolerances, glass design, we design only in as per AS 188. We don't design ASTM 1300 because India is practicing ASTM 1300. ASTM 1300 is experimental code where it allows 8 glass break for 1000 glasses, which is vulnerable for investor. So don't practice ASTM 1300, practice AS 1288, which is adopted in EU NBC 2016, and amendments happen in 19 as well as 20. So these are the codes, you can see that. Coming to what is complex facade. Facade comes with the 3D geometry, which is not a rectangular or square or flat surface. So these are some of the examples of the globally done complex geometries. You can see that there is limited but no repetitions. So also warped geometries where glass is getting flat and you get warped. How you accommodate and design the geometries of the facade element in a warp conditions or curve or segmental conditions. And also is a simple geometry, looks when you design like a ball or any shape, but is too complex in designing and putting in metal and glass together because all are straight and flat and stiff materials. How we make it a complex, such a material, how we bend to the shape. So this is the first Crystal Palace, the world's first curve building in 1851. And is single curve. Today you can see the BMW showroom in Munich is a twisted. The geometry is changing like anything. Also you can look at what constitutes a non-twisted facade, which is come to the surface is single flat plane, but surface can be single or double curve, and it can be four-sided panel can across the surface without a steps or without a line or without a straight point. And also the surface is not developed from a flat surface. It is developed from a concave or convex or whatever shape you build it, and it has to be developed from the plane. You make any curve, you make a plane, develop the model, develop the engineering, then try to shape it out. Otherwise impossible to get it done. You go to the site, you get to one corner is a 1 mm joint, other corner is a 10 mm joint, you are unable to accommodate it. Coming to rectangular panel will be easy, but we also integrate rectangular panel into complex geometries by cold bending. We adopt, in our design, we don't adopt a traditional approach. Architect give the drawing, just put the detail and don't do that. We specifically study the geometry study when comes to any shape out of standard shapes. So we do a geometrical studies, address with the material availability in the industry. People design complex geometry by 5 meter by 3 meter, glass is not available in India. So some people give the detail, then finally they come back to us how to get it done and how to do it. So upfront from the concept schematic stage, please study when come to complex geometries. So we do a geometry analysis and design as per architectural design intent. Then we provide all modulation analysis. Maybe we need additional joints required, maybe additional steps required, or you need to bend some locations, then only able to get the complex geometries. See, look at the geometry studies. These are steps, examples of such a buildings. You need to define the grid first, and you need to create the reference for every grid related to levels, horizontal levels and vertical levels and floor levels, and interface with in mm. Be careful, interface with in mm, otherwise you cannot fabricate and install. And this is a panel define and understand geometrical relationship. We study how much is the maximum gap coming, and we use a mathematical formula to derive the panel modulation with the geometries, and use the grid with the datum line, with the reference points, and also we take more notes to get the panel modulation design and fabricated. These are you can see then we identify the 3 types of modulations coming into the building. One is a warp, one is inclination, and another is a perimeter. So how are you going to integrate and address everything? So you need joint connections, you need integrated patterns, everything. To do that, are you able to do these shapes between floor to floor? Your sharp corner you are unable to connect with the slab. So you would investigate and modulated, integrate with the 2 triangles into one rectangular trapezoidal panels, and you would get it done this. Otherwise, very difficult to get such a complex geometries. So we used a specialized engineering softwares to adopt, but there is no way to get other way done. So you CAM or CAD integrations, every element need to be modulated and modeled, as then that used in the building information modeling integrated, and we use sometimes grasshopper, rhinos and integrate together to get the model out. Again, that helps you to get the panel sizes. Then engineering that such a panel size is a very another task. So this is a connection detail, as I said. You need to make it the connection detail such a way that it has to be performed for all air and watertight and other things. And need to use, as I mentioned, all parametric design will be get done. And you would draw each panel independently and mark it in elevation wise, floor wise, then only able to integrate the entire elevation come as a complex geometry. And you need every corner, need to be individual detail to be done. So what is the issues faced by the designers is this need for differentiation between flat to complex, break with the traditional form. Traditional form, you just get a rectangle, we have to break it with the complex forms, and also convincing owner developers, increase the cost when you change from flat to complex geometries, there is a cost to it, and also accommodating construction sequence. You design a complex geometry and you cannot design and straight away go the construction, finish the structure, and then you want to do a complex geometry, then you face with a lot of problems. So when you come to complex geometry, you have to hand in hand work with from concept schematic stage until detailed design to integrate and execute the facade element. So the structure, whatever requirement, offset or recess or slab thickness, sometimes edge condition, you put a 250 mm slab may not require. Sometimes the beam to be sloped in a triangular beam to receive the inclined panels, or outward inclination or inward inclination. So the structure to be well coordinated for interface with whenever complex geometries come. So in India, most of the cases, the structure finished and go by facade. That works for rectangular or square building, but not works for complex geometries. And also reverse in trend of all the industries now in facade data. But you need any complex geometry, you need a high tradesman and skill for fabrication and integration. Otherwise, it's very difficult. And material availability locally check. If you imported everything on complex geometry, something get wrong, then again you would import and use the materials. Case studies with a different type of complex see there are few types of geometries in complex. One is a fish scaled facades, there is a stepped and stripped facade types, and as well as the twisted facades, and as well as triangulated modulations, then as well as cassette type facades. So look at this is a fish scale job. These are three major fish scale jobs globally. The right hand one, the Park Place in Dubai, which we have done. You can see how the geometry is this. So it's a 60-floor tower, and it is a double curve, and it twisted. Don't think though that is a curve. It's a double curve and twisted. And these are the sort of ram radius geometries. We have to put the radius floor-wise from ground to the roof, and set out the curves, and integrate and change every floor. The radius changes every floor. So you're putting a panel to this radius and putting the panel to other radius, all interfaces to be addressed for air and watertight and complete conditions. And you have to consider floor below and floor above. So these are the radial mullions where we adopted with the formulas here, we calculate and get it done accordingly. Then we also study the warp studies and analysis. Maximum warp in this building is 50 mm. So 50 mm warp is an impossible task. So you need to know how to detail it, how to engineer it, and how to get it done, this detail warp. So we color it on all type of plot panels. Then again, how much warp is coming in the envelope. So these are the some of the details. Gutter to be designed for drain when rain comes. So we cannot have 100 systems. Cost is 2 times of the project cost. So we use one system, because then we provide more adapters to integrate all radius and curves and warps and get it done. See, this is the incline adapters rendering image. So you can see that how much warp is going inside when the curve comes. So the advantages and disadvantages here, you go for this warp, then you aesthetically you're compromising, so forced to put a flat glass and you have to recess the panel in a corner, it looks ugly. So we have to design the glass to meet the complex and flat joint. So panel sizes are not uniform, then you end up with 8,000 panels, independent panels. So we address with one single panel with a cold bending with the flat glass. So you would do very thorough calculation required. What is the deflection limit? What is the yield, maximum yield strength? And in between you have to balance to, after fabricating you can cold bend and install. That's what Gary done. Then coming to strips facades, and this is the, I take the Sama tower because I worked in Dubai time. This is a 50-floor tower. You can see the ground floor is one plane, the exactly mirror on the roof terrace. Is a twisted. You can see the ground floor. You can 25th floor is exactly rectangular, and the roof terrace is a mirror of the ground floor. So coming to this, you see the X direction at the edge of the slabs between the 25th floor above and below. What inward inclination happen at the ground up to 25th floor, and what is outward inclination happen above 25th floor. So the glazing runs between these slabs, you have to, because no other way you have to get to install the panels, and these, it has to be parallelly run because the geometry is such a geometry, and also is a crank glazing where you need to parallel to the slab and edges, and it has to be maximum offset of 440 mm from ground to the 25th floor, and again there 0, then again 440 mm on the roof terrace offset. So it has to be designed such a way. You can see this option 1, we tried all the options, then finally we end up with the fully unitized with additional adapter, sill adapters, which you can see the corner conditions, every corner shift. Either you would consider a sharp corner with the floor shift, or you would consider cantilever out the facade, then connect the other floor, or you have to terminate in a 90 degree. So architecture not agreed for option 2 and option 3. They wanted the geometry should follow option 1. And we integrated tell we need to provide some fin to offset in install, otherwise you cannot get the geometry out. So we did a stepped out facade element design, and we did the design and executed at site. This is the image at the bottom, you can see executed at site. The advantage is a flat glass, no many number of type of panels, simple and cost effective, so we done with adapter. But the system technology is slower because of the adapters, and is a step, mild step coming between floor to floor, but in a look at the under meter, you won't see the step. So is only the disadvantage in the design, which architect agreed, then we move forward with the system. So it's economically done with a one single panel size, with adapter. Coming to twisted facades, as I mentioned, is a cold bending. These are some jobs, like whatever seen in New York and as well as in Netherlands. And Ocean Heights, we did the project in Dubai. Every floor shift, you can see the rotation of the floor. The floor design is the same, but it rotates like a clock, and it has a flat slope and is warped. And we also did a geometrical analysis, what is the twist, overall step, and warp in how many mm. And also we derived to warp analysis with the 20 mm. The other project is worst, 50 mm. So how to get the panel for the warping. So we studied 3 options. With a glass truss and glass distortion will come when you do cold bending. Then warranty and breakable when you are always under stress. And what is the minimum aluminum cost has to be implemented on this. And no more glass truss, less glass distortion, warranty and minimum cost, as well as no glass truss, no glass distortion, warranty is safe, and high aluminum cost, because you need to step every junction. So we recommended option 1 by cold bending. So again we calculated and pulled the panel. If a facade is like this, when you hook on to the next panel, then we stress, tighten and pull it out inside 50 to 25 mm and tight locked. So the panel is under stress by pulling and permanent fixing. So that can be done, so you saved a huge cost. I think time running out. So I speed up. Then again, triangulated modulations. These are the building we done in Gurgaon as a case study. Unfortunately, this project not taken place. ENY building under morphogenesis. But we did the documentation, I present it. There is every floor shift 2.5 meter out. And this again is a circular way, like egg shape. And it has a geometry, whatever comes in, whatever I explained in Park Place. I skip it fast. So this is a triangulator only workable because the shape and the radius. So we made a trapezoidal bent panel as a single panel to install. You can see that because we did a hook-on system, so this can be tilted and it can be installed like that. It can be installed like this. Slightly twist, trapezoidal bent to hypotenuse. This is one of the Ratan Tata's visionary project. And you can see this job is completed and it withstand 2 cyclones, withstand 2 floods in Chennai, and is successfully standing still because his vision he created with his own classmate Carlos Uruguay Ward he is from Uruguay. And this is a completed project. We have 5 geometries, and out of 5 geometries, 3 of them curve geometries. And you can see that, and on top the butterfly, and this facade is cantilever 17 meters. You can see this. And we have a deflection on the 17-meter cantilever is 90 mm. Whatever you put interior fit out, whatever tile you put, it will crack every time. Any maximum wind speed come. So we have to reschedule the deflection to less than 20 mm. And we did a plan geometry. We have a wishbone brackets we designed, and this is geometry plotted. That time we did not use beam or anything. It's completely done in 2D, and we successful and tested 9 kPa and still stand still. These are all geometry plotted and integrated into one plane. And panels are standardized and installed. And this is a wishbone bracket where such a 17-meter cantilever, we reduce the deflection to 20 mm, less than 20 mm. And this is a crown on top of it and installed, and spine and elevation. Okay. Coming to evolution complex, there is no regular grids, when it comes to this. This is a Bangalore airport extension. The bull nose is, they wanted such a way in 3D curve in a solid aluminum panel. So you would weld and install. Okay, I run it. So just this is a standard rain. I think it's a huge presentation, so they are running out of time. So the twisted facade. So this after the manual. Give me 5 minutes. I finish. If you don't mind. Yeah. So this is a parametric modeling for freeform roof and how it's integrated. I just run it because of understanding everybody here. When you design such a thing on the top, you will get a segmented panels. You will not get the curve, whatever design. Bottom you have to streamline. It has to be trimmed in facade glazing, and it has to be integrated, and you would get this form. So when you put a flat panel, it will come like this. When parametric done, it will be shaped like this. Then either rectangular panel or trapezoidal panel or triangulated panels, or it can be form of cold bending. So these are some of the gaps which we address and design, and these are the fish scale we form, freeform and integrated. So these are the sections and the done. So these are the installations of the panels in various levels. So this is a building maintenance unit. So I think it's a car, you have to maintain a facade like any time. So I think we're running out of time. So the presentation is with you. I think is a key subject. I just touch on few jobs of the Hyderabad. What is a hidden marvel structures in Hyderabad. Can you go to the last 5 slides? No, I'm not taking any questions. I can interact with them. No issue. I put my contact details. Just okay. But go back. Hyderabad. Go back. Go back one more time. Yeah. Okay. Hold on. Hyderabad projection. Okay. Go next. Okay. Hold on. See, this is one of the iconic project in Hyderabad, which maybe Hyderabadians not aware of it. This is a double skin facade in India. No, not done anywhere. All four side double skin, and every facade you can walk. And there is a the tall single standalone steel structure of 60 meter wire perforated fabric on top, which is nowhere in the world, is in Hyderabad, which is done by us for DCS. And this is a catwalk in between the building. You can see that, where you can see between you can walk in every floor on the perimeter of the facade. And this is a catwalk detail. And this is a Wipro Gobanpalli, 100% brick. 300 by 100 by 100 brick. And these are the bricks, completely integrated in unitized panel and installed in Gobanpalli, and no seal and anything. Grouting done and installed, cement grouting. And today, 3 years, 5 years, 0 failures, because latex additive did get it done. And this is Arabindo Galaxy, which is the tallest precast concrete structure, and the panels are, die grids are installed because of the precast tolerance are huge. And also Hyderabad Airport we done. We done the Statue of Unity. Quick on this. This is Sardar Vallabhbhai Patel statue done in 1:1 scale, then reciprocated into the 187 meter height. And sorry, this is his face, this is his leg, what size you can compare with a human. And this is the Statue of Unity, the terrestrial steel all done by us. And coming to the integrating the panel, we done this terrestrial steel. And these are 537 panels, independent panels. Each panels are independent. And these panels are, and every panel has 11 to 15 bolt nut connections, which each and every bolt nut weld is certified by us. And today, this is the team. We worked with, we are the lead engineers with the Statue of Unity, worked with the Turner and architect Michael Greaves, and we completed the job. And Statue of Unity is the Iron Man of India. I'm proud to say that I am part of it. And standing tall for the Indians. And as well as this, thank you so much. Any questions, please ask me. They are running out of time. Thank you.
Sir, one question, sir, here. Sir, here. Sir, here, sir. Sir, can I ask, sir?
Yeah, please.
Yeah. Nice presentation, sir. Nowadays, we are studying the fragility index and the vulnerability index for the multi-story.
I don't know who is speaking.
Here, sir.
Okay, sir.
Yeah. This is Dr. Narasimha, sir. Yeah. Nice presentation. Nowadays, we are studying the fragility index and the vulnerability index for the multi-story buildings. Is there a height criteria for the necessity of these studies? Height criterion. That is up to which stories, the number of stories.
See, height stories depends on the authorities. Depends on the soil condition and foundation, all other things, structural, how you design, and how the locality with, we are in city, all our Indian cities are, the airport is within 20 kilometers. You have takeoff funnel, landing funnel, and emergency zone, all need to address with high rises. You can build up to 300 meters is allowed in India, in Bombay and other countries.
My second
I'll
question.
talk to you in person.
You can please address your question in person to Mr. Arumugam. Thank you for cooperation. Thank you, Mr. Mahesh Arumugam, for this wonderful informative session on the facades, especially how we deal with the facades with the external skins and the double skins. Quite impressive. Thank you so much for the presentation. And now I call upon the newly appointed Secretary General, Engineer Rajendra Kalbaviji, and Engineer Sudhakarji to please come forward for felicitating our speaker, Mr. Mahesh Arumugam. A round of applause, please. I know we are coming in between you and the lunch, but please bear with us. We just have one more session to go because it's continuing the flow of the architectural subject. So we'll just have one more session and then we break for lunch. So kindly bear with us. I know there must be little rats nibbling around our tummies, but please bear with us. Just next 40 minutes, one session. So, thank you so much, gentlemen. And the next session, much awaited session personally for me as well, which was supposed to be yesterday, but we now have it today. The topic is super tall buildings, the next generation. We all know that space is limited, but the requirement goes up every time. So instead of going horizontal, we now go vertical. And let's listen to this from architect Marshall Strobala, who's here with us to delve onto this topic further. May I request architect Marshall Strobala on the dais, please? So he's born in the year 1961, and he's a highly accomplished architect with 34 years of architectural expertise. He holds an undergraduate degree in Design and Fine Arts from UCLA and a graduate degree from Harvard with a Master's of Architecture. He's an affiliated fellow of the American Academy in Rome and has spent 19 years at SOM Chicago, where he served as an associate partner and studio head. I wouldn't delve much on his achievements now because we will hear it from the man himself. Thank you so much.
And this is forward.
That's a slight change also. You'll be able to change it.
Okay, great. Thank you. Oh, sure. Oh, then I can walk around.
Yeah.
Well, first of all, I'd like to apologize for not being here yesterday. It's really the fault of Thai Airways. I was on time, they weren't. And I humbly apologize. It really ruins the cadence of everything. And we'll try to be very quick so we can get everybody to lunch on time. Can you hear me? Okay. I've been doing this for 33 years. I am now a professor of architecture at China East Normal. I've been doing high-rise buildings all over the world, from 20 years at SOM to 4 years at Gensler. We've had our own company for the last too many years. I'm 62 years old, and I love what I do. I get up in the morning, and I get to build models. I get to draw pictures. This is a private house in Shanghai. It's a small house, only 10,000 square meters. The floor-to-floor is 8 meters. So it's a tiny little abode. Under construction today. I'd like to start off by saying the wind tunnel presentation was fantastic. For all our projects, we use wind tunnel people. We also hire fire life safety consultants. All my projects I've ever done have sprinklers and are very safe. I'm always worried about fire. And we also use facade consultants like Meinhardt to help us with the technology of the facade. We do laboratory buildings. This is a GMP building. The architects do drawings like this that we transfer to people like Meinhardt. And we started doing a lot of low-rise buildings and campuses. This is a university in Shanghai that would be the largest zero-carbon building in the world. It's about 340,000 square meters of space, and it's only 3 stories. We wanted to build it out of bamboo beams, bamboo columns, and that creates a whole new fire life safety issue. We always try to make the projects feel like where they are is important, not just design something that I like, but try to find what we call contemporary culturalism so that the buildings could look like they've always belonged there. You may not know me, but I started doing buildings that people recognize 30 years ago. This is the Hong Kong Convention Center when I first came to Asia. This is the Suzhou Convention Center. The spans are 81 meters. Quenzhou, this is a bookstore. I have so many projects I don't know what to show you. This is our dam client, Gujuba. They did the Three Gorge Dam project in China, and I like calling all my clients dam clients. This is an office building in Houston that has wind turbines at the top. In Dubai, Shenzhen, Sanya, Kuala Lumpur, China. This was the 7th tallest building in the world when it was built. And I show you these buildings not to brag, but to show you they're all different. They're not one design fits all. The design has to fit its climate, has to fit its people, has to fit its location. There's 3 clients to every project. There's the people that pay for it, the owner, the client. The second is the city where the building is. It needs to respond to Nanjing. It needs to be a part of the city fabric. And it also has to satisfy the thousands of people that use the building. This is, I call this Double Happiness Tower. This is the 3rd largest building on the planet in Cambodia. The client wanted the world's tallest twin towers out of gold. And of course, the Shanghai Tower. I've spent 17 years working with this client. And the world's tallest building, the Burj Khalifa, that I did at SOM. So I've been doing kind of projects on a basis that they all get more and more complicated, as we saw by the facade. And I think I have the greatest job in the world because I get to work with all of you. All the civil engineers who become structural engineers make me look good. So I'd like to thank you. Thank you very much. You make me look good. And I apologize for all the idiot asshole architects in the world that treat you poorly, because if they were really smart, they would be here applauding you and thanking you every day. So, this last project I'm going to show you today is what I call the next generation of office buildings. Now, office buildings are kind of ubiquitous. Who here loves their office buildings by show of hands? Who loves their own office building? I should put on my glasses so I could see. Okay. How many people hate their office? How many don't care? How many people don't speak English? Okay. This is what I joined SOM in 1988. Everybody wore white shirts, ties, and jackets. I haven't put on a tie or a jacket in 12 years, mainly because I'm too fat and it doesn't fit. And I ruined so many shirts, my wife cut them off and said you can only wear short-sleeve shirts now, because I would put ink on all my shirts. But this is an office building. The green makes you money. The black costs you money. So the idea is to minimize the black and maximize the green. Pretty simple. This is not fantastic. This is a bad building. Big core, small. This is even worse. Offset cores are okay, but they have their problems. Side cores are okay. Sometimes they actually work with the climate. And odd-shaped buildings, whatever you want to do, you could build. So as a performance design, tall buildings are just the same floor repeated. So when people say, Marshall, design me a high-rise building, 100 stories, and we'll give you $10 because you design the lobby, you design the top, and 99 floors in between are all the same. You don't have to do too much. But more work goes into a super tall building than you could imagine. All the people in this room I met a geotechnical engineer this morning, fire life safeties, wind tunnel, facades, MEP engineers, et cetera, et cetera. So lease span is very important. From the inside of a building, the distance from the core to the glass is very critical. Most architects don't even think like this, but when we design a building, we actually design the core and then add a lease span to it. So the lease span is modular. The best lease span is about 12 meters. From a structural, MEP, and architectural standpoint, the 12 meters is the one in the middle. But you just don't move the facade by 100 millimeters. You have to move it by about 1.5, 1.4 meters. That module is very important. So 13.5, every building I did at Canary Wharf had to be 13.5 meters, because that gave you the most people in the least amount of space. In Germany, they limit the glass from the core to 7 meters. So a lot of the buildings in Germany are very glassy and have daylight, but are very costly because they have very big perimeters. So I did this building for a client in Chengdu, and he said, ugh, where's all the fun space? Clients today like flex space. These buildings that eBay has done and Tencent with bridges and places for people. You see Google's headquarters, and everybody talks about the quality of space, and your building doesn't have any of that. Very nice floor plates, very efficient. The VT transportation system works well, but there's nothing fun. There's no fun spaces. So we started doing a lot of research on what worked in terms of spaces, and we started coming up with numbers for how many people we could fit to show that our buildings were better than our competitors. This one is Taipei 101, and the first thing someone says, make a bigger floor plate. The 8.2 number, the lower that is, 6 is fantastic, 10 is terrible. So someone says, okay, Marshall, who cares about that? Just make a bigger floor plate, you'll have better efficiencies. But it's not always true. This is 8.1 for the Sears Tower. This one right here is 10 for this odd building in Kale. I can't remember the name of it, done by some architect in New Haven. But if you'll notice, this little tip down here was added because the efficiency was so bad. The original design was 12. And they had to actually add this just to bring the efficiency up, because this designer didn't start with the inside to outside. So this goes on for a lot. Jinmao, 9.1. This one was, my old boss did this in, I think, Chengdu. The odder the shape the building gets, the least people you could put on the floors. So this is a very efficient design, both structurally and from a layout, but it may not be a design you want, because what we just saw, Meinhardt showed us these curvilinear, twisted buildings. Everybody likes something sexy. This is a good building, 7.5. Very, very good number. But as you go up the building, it gets worse. It gets about 9 or 8.5, and then it gets worse as it goes up. And this is just a number to compare the buildings. This is not an actual layout from the inside. The Shanghai Tower, which I designed, has a very good number. This building right here, I discovered as being one of the worst buildings I've ever seen designed. It tries to look like a piece of bamboo. I don't have a problem with that, but what I do have a problem with is, why are some columns round and some square? And why are the columns so far from the facade? And why is the space so bad when I have a symmetrically square outside and then I have a rectangular core? So we were asked to look at this building, and we made a lot of recommendations. And you can see as the building goes up, it gets a little smaller, and you would think the bigger floor was more efficient. But actually, the bigger floor is not as efficient because it adds all these spaces that are really hard to plan around the columns. So what we did is we worked with a structural engineer. I always work with structural engineers whenever I do a tall building, because remember, engineers make architects look good, and I'm not a dumb architect. So we rearranged the structure in different organizations, and then we looked at it in a performance-based design element. So what was designed and what was built is pretty poor. Using mega columns, and the option 1 was actually the best. We got the best layouts because we have big spaces that are very flexible. Not that interesting, and it's something we have always known and looked at. But then the Shanghai Tower, how does that work based on what I just showed you? The lease bands are basically within the columns, and what's outside the columns is sort of bonus space. So when we worked with the client on this, we were always very in tune with designing the core. The space around it was basically added to the core size. My office in Shanghai is this. We're the world's highest architects. We're at 256 meters high on the 56th floor. So this is our office in Shanghai. This is our workspace. This is where you could put a lot of different things in. What we have is storage, meeting space, lunch space, flexible space that could be, we actually use this as a photography studio to take pictures of our models. And then we have offices, and we have sort of workstations. And this is a high desk, so people are actually working at a high level. So when I come by, I'm talking to them face to face. And this was a product Steelcase did to do call centers, to minimize people's space. But then when you talk to them, they don't have to stand up or you have to sit down. You're actually looking at their computer at the same height. It's called a high desk seat. And we've been using that for 10 years now and love it. So these are just some photographs of the office. Nothing special about it, just a bunch of architects working. We used to have a partner that was a landscape architect, and he insisted we put this green wall in, but it didn't face the window, so all the plants died. Lessons learned. If you want plants in your building, make sure they face the windows, not the corridor. This is just an example of how we design from the inside out. So these are two towers, 250 meters in height. Each is about 125,000 square meters. So you could pick a floor size for it. 2,500 is a good place to start based on one fire zone in China. 3,000 is a new fire zone in China, so you don't want 3,100. But it used to be 2,000 was one fire zone. So 90% of the buildings in China were based on 1,900, 1,800, very small footprints. They've allowed that to go up. So basically the core is divided, is mostly elevators. You saw the VT, the vertical transportation lecture yesterday. And cores are mostly elevators. So in tall buildings you have to use 4-packs, 6-packs, 8-packs, whatever. And this is rectangular. But architects all want to do weirdly shaped buildings, circles and triangles and twisted trees and what have you. This is the core of the Burj Khalifa. The red shows you all the elevators, mostly elevators. A core is a bunch of holes with a wall around it. This is the core of the Shanghai Tower. There's about 35 slots for elevators in this core. It's about 32 meters by 32 meters. So the core of the Shanghai Tower is 1,200 square meters, which is bigger than most residential buildings by itself. We have 30,000 people a day we move through this building. So we designed the core. We could do that mathematically very easily. If you know the number of elevators, you could mathematically figure out everything else, but then you have to add that to a size. So we draw our cores first. Then we add the lease span, and then we add the perimeter. We check the areas, and we move forward. We always have an area that we could adjust and move in and out a little bit to make the area work out. But the lease spans on the two opposite sides are consistent. They don't change. So in this, we had a 12-meter lease span. We have a core. We have a very, very simple building, square building. But the core is very complicated. It basically has to have hallways, toilets. We use the dead elevator zone for toilets. And this one, the low-rise lifts are here. We have 6. 6 is the mid-rise lift. And the trick to designing a core is how does the core get smaller as it goes up? Structural engineers know this. Architects know this. Mechanical engineers know this. But this is what the problem is. You end up with these very odd-shaped buildings, and this is the top zone. We try to give the space back. We try to make the space from black to green so we could use more space at the top. But what we have is we have this odd shape in the center that started out very square, so the structure kind of changes as it goes up the building. The engineers now have to do more work to make everything work and keep the building from flexing and moving, et cetera, et cetera. So this is a pretty standard way of doing a building. We've been doing this for the last 30 years. No one's complained too much about it, and everybody sort of builds buildings like this. Okay. And then the architect shapes the buildings, and then we show images like this and how beautiful our building is. But we like to think of our buildings as very performance-based from the inside out, not the outside in. So, the world's tallest building, we started that in about 2003, 20 years ago. And the idea was to create a very efficient building. And what I want to focus on the Burj Khalifa is the 3 sky lobbies. Most buildings have no sky lobbies. A sky lobby is, how many people know what a sky lobby is? How many people don't care what a sky lobby is? A sky lobby is a place you could switch your elevators. I'll show you in a minute. That's a picture of me when I was much younger and thinner and less gray. The Burj Khalifa is mostly concrete with steel on the top. It changes from concrete to steel about 560 meters high. So it has a hat that's 270 meters high. So am I taller if I put mousse in my hair? On the day with mousse, maybe, but usually not. So the core is very tight, very compact. This is a residential building. Residential buildings have very small numbers of elevators. The ratio is about 1 to 6, commercial buildings to residential buildings. And then the vertical pieces in the Burj are all tied together by horizontal slabs. Nothing really fancy here, but a very, very good system of structural design. Because as you look at each floor, we just stop building parts of it. So nothing is transferred, everything is very simple, and we just stop building portions of the building, and then the building actually gets smaller as you go up. It started as 100% residential, ended up as office building at the top, which is another problem for vertical transportation for another lecture. But what it is it's an inward spiral. It gets smaller and taller as it goes up, which actually reduces the wind loads and creates the look of the building, which is the lessons learned that became the Shanghai Tower. So, we have 3 sky lobbies. Level 43 is above the hotel. There's a hotel, an Armani hotel, from about 6 to 42. And then there's a sky lobby that takes me to 43 and then up to 72. So the first sky, these are the freight lifts. The big one, the 2 on the left are sort of the big freights, and then the hotel service are on the right over there. And then these are the hotel passenger lifts. And then what we have is sort of straightforward vertical transportation on this side of the building. And the hallways are 80 meters long on level 5. This is a rather big building. It's about 450,000 square meters above grade. The first sky lobby is approached by the 3 on the outside of the core. Those 3 lifts take you to 43. Then you transfer around the core and you take a local set of lifts. And at this floor, which we call a sky lobby, has a health club at the tip. So there's a wonderful pool on the outside, there's a health club, and there's a party room, and that's where you pick up your mail. So we transfer here, we have to take 2 sets of lifts to our floors. So we have 3 locals and 3 express lifts. And this repeats itself for the next set of passenger lifts. So these 3 lifts take you up to 73, and then 73 to about 119 takes you up there. It's not rocket science, it's pretty simple. But what it does is it allows me to make my core much smaller by not starting all my elevators at the bottom of the building. And the time it takes to get here is faster than if I took elevators from the bottom all the way to the top, because either I'm stuck doing faster elevators or more elevators just to meet the same performance level as I have here. So we want to use the minimum number of elevators in the building. I think I can't remember, I think it's about 36 total elevators in this building, where the Shanghai Tower has 117 elevators in the whole building. So, the top floor is actually an office building, and we use the top deck of a double-decker. These 2 lifts are the observation lifts that take us to 123 or 124. But the top part of the lift is for the public, the bottom part is for office, who then go up to 124 and then take local elevators to the top there. So people are sharing a lift they don't even know they're sharing. Okay, so the technology was there. We even looked at doing triple-deck elevators in this building. No one really wanted to do that. None of the big companies. And so we had to back up and only do double-decker lifts. Okay, so you come around and then you take, there's, originally it was 40 floors of residential. We switched to 30 floors of office, different floor to floor height. But it was a business decision. Mohammed Alabar said the penthouses in Dubai weren't selling. So he couldn't sell the penthouses in the sky at the top of this building, but people said if you had an office up there, that would be great. So we have boutique offices at the top of the building. So the shape of the office is not that efficient, but it's a show office where you go up there and have a conference room and take your clients off and show them the world of Dubai. You get the view that you have to pay 200 dirham to go to the observation deck. So these sky lobbies actually pay off in terms of smaller core, faster arrival at your destination, and it became an idea. We tried to sell this idea in Korea in 1996, and no, we don't want it, even though it actually provides better space. The Shanghai Tower I've been working on with this client for the last 17 years, which is why our office is there. So one of our biggest clients, we just have to go down to the 10th floor, which is kind of a pain in the ass because we have to get to the 10th floor, we have to take 3 different elevators in the building, in the same building. That one I didn't think about. But from the facade standpoint, this building has a nice twist to it for reasons that reduce wind loads, and every single panel on this building is flat. No cold bending, all unitized, very, very simple, cost-effective. The only thing we had was an RF chip in every panel that located it on the building. I was afraid there'd be big pimples where the facade wasn't smooth, but the contractor did a beautiful job. When we start designing a building, I always look at what we have to do. Areas of refuge, mechanical floors. This is a diagram that shows you where they are in the building. It's mostly office space. There's a little boutique office at the top. Because your core gets very small at the top, we could fit a lot of extra elevators in up there. There's a hotel at the top. Our big ballroom is down on the 5th level. The observation levels are very valuable. One observation level is equal to about 10 office floors in terms of rent and money back. So the more floors you can get in your observation experience, the better off you are. They pay off very, very well. And there's 3 super talls within 50 meters of each other, Jinmao, WFC, and Shanghai Tower. And we actually put our hotel lobby at the height of our competition's observation deck. So you can go to our hotel lobby to look at their observation deck. So everybody comes to our building to look down on the neighbors. There's 5 sky lobbies in this building. When I presented this to the client, no, we're not going to do that. That's a dumb idea. And it took a long time for them to buy into this concept. A lot of it had to do with money. A lot of it had to do with function. What could we do on those floors? Because this is the 8th floor to the 126th floor. And getting the core to shrink down and also the building to shrink down is a real trick. The core itself gets smaller, thinner, and changes as it goes up through the building. This is just the office. I won't bore you with every elevator in this building, but these are the office lifts. The first zone is 10 cabs that take you from ground to the first zone, like any other building. So that goes from ground to 8 to 12. Then the next zone, 22, you take an express elevator, which is 8 cabs, 4 on the first floor, 4 on the second floor, double-decker cabs, so I could double the population to this zone. And then what I can have is an amenity floor here, because I have a bigger floor that I thought would be restaurants, some conference rooms, maybe a health club, some things like that. And what we have is we have these amenity floors that are the space between the double walls that people love. And that's my wife in the pink blouse. And my dentist is on this floor, on the 22nd floor. There is a health club on this floor. Here's my dentist. And there's a hot pot restaurant. And there's another restaurant that just opened. So there's a lot of things that happen on this floor that you wouldn't expect. But it's a transition floor. On the 37th, there is an art museum. So the client put an art museum up here, and it's the same system. You take 4 cabs, but they're double-decker cabs. That's 8, and then locals are 7. So when you go into this building, there's never more than 7 buttons in the elevator. How many here have been in an office where they push the button and someone comes down, and all of a sudden you have to wait 10 minutes before you even get an elevator? The elevators here come at less than 30 seconds. The criteria here is very high. So, there's a museum. People come to this museum all the time. That's the landscape architect, John Wong from SWA, and there's a tea house up on this floor. I skipped the 5th zone because I want to come back to that. Zone 6 is a couple restaurants that are very high-end. That is the same way. You take an express and a local. And there's a very high-end Chinese restaurant, and there's a French restaurant that serves this gastronomic cuisine, foams and duck eggs and all the stuff that have no flavor but cost you $1,000 a plate. You have to sit there for 4 hours. I made the mistake once. So Zone 5 is the same thing. We take the elevator from 1 and 2 to 52 and 53. Now what's really interesting here is this is a big floor. This floor is about 4,000 square feet, 4,000 square meters. And you have to go around the core from the express to the locals. And the people in this zone, about 3,500 office occupants if it's 100%. So those 8 cabs had to service 3,500 people. Bear with me, the numbers will make sense. And right now, it's sort of in the middle of the building, 243 meters high. And a bookstore, a very famous Chinese bookstore, took the whole floor, which I never thought you could have that much retail. You could have 3,000 square meters of retail on the 52nd floor of any building anywhere on this planet. You know, I thought it would be 2 restaurants, a conference room, and a coffee shop. No, 1 bookstore, and 7,000 people a day come to this bookstore through elevators that were only designed for 3,500. So double the population is moving through those elevators every day than what was designed for it. What happened? Did we over-design? Office transportation is peak, morning, lunch, and night. Retail is all day long. So what we really have is we have a very efficient system for the office, and when it's off-peak office, we service this. 7,000 people a day coming up there. It's absolutely amazing. I walk through this every single day. And what I learned is there's no problem. Sometimes the line gets too long because there's too many people at lunch. But what's interesting is there's a back door. I could go to the 2nd floor and take the elevators from 2 to 53 and come down the elevator. I have a back door that I know about because I live in the building. Big, big revelation. Can we then take this and take this idea rather than walking by the elevator? If you look at this drawing, I don't go into these beautiful atrium spaces. I kind of walk around the core and glance at them. The idea, can I put the elevators out to this atrium and make something of it? So the idea came from this bookstore, the 7,000 people. This is where I go to lunch on 53. It's a little steakhouse. So I have to take 1 elevator and 2 escalators to get there. Wonderful view, delicious food. And the elevator system is the same as all the others. Okay, so the idea comes to me, what is the next generation of super tall buildings? Looking at what we did in the past 30, 40 years of tall buildings, and I'd like to give a small shout out because I usually talk about structure and wind, and some of the best structural engineers in the world have come from the Bengali coast. Hal Iyengar, Fazler Khan, Joe Colasso. There was a whole bunch of learned engineers who went to the States in the 80s, 90s, in that range, and actually developed the structural engineering of tall buildings. So you should be very, very proud of that. So the next generation is if you could create a building that tenants will line up for, because a big building like the Shanghai Tower attracts small tenants like me. My firm in Shanghai is only 50 people. We're the highest architect in the world. We pay the highest rent, but there's only 50 of us in that office space. We're not that big. I would love my name on the Shanghai Tower, but I can't afford it. But people come to our office because we're in that building. We look like we're a big firm. We look like we're a KPF, an SOM, a firm of 500 architects. That has value. Most of the tenants in super tall buildings are small tenants trying to look big. So, this idea goes back to this building, and what we did is we said, okay, this building started it, where we said, okay, well, if we could use spoilers in the wind to create less force on the building, and then turn these sky lobbies into places of arrival and special bookstores, restaurants, what have you, put slots in the building to reduce the wind loads on it, we have a double effect. Then we have outdoor space for tenants, for all kinds of things. So this one had 4 sky lobbies, fundamentally very much like the Shanghai Tower. So I don't have to go into the detail there, but the atriums could bump out, they could come in, we could tie them in with the structural outrigger system, a lot of things. So this we call the double happiness tower. The Sky headquarters is basically from this competition that we did in Guangzhou. And we started doing master plans, which, how do you do a green master plan? We just say all the buildings will be green? No, we look at the number of buildings. So on this site, we worked with a partner in Guangzhou. They wanted to do 4 buildings. We wanted to do 2 buildings, and it was a big fight. But what we did is we actually said, okay, let's look at this logically. What's the right thing to do? 4 buildings or 1 building? And we actually convinced them that 2 buildings was a green thing to do. Same number of elevators, same number of area, but different facades, different exiting, different MEP systems. So we could look at this and say just the facade alone by area, doing a single tower is the right thing to do. But it's also too big of a building. The lease span starts to be 18, 20 meters deep, which doesn't make a whole lot of sense. So we started looking at maybe splitting the building into 2 buildings and twisting it to line up with the historic building on the next site. So this little twist is not so important what we're talking about here, but we're talking about dividing the building into 6 zones, into 5 semi-sky lobbies that are actually coupled, and what we do is we correct the shape of the building to actually have these double-decker elevators where now I'm stacking half my express elevators on top of each other so my core gets smaller, and then I'm also stacking my locals on top of each other. My core gets smaller. And now what I have is a western-facing building. This is the facade study we did on how we put the facade together to improve performance. And the only thing I'll show you here is we did minimal vision glass, reduce the amount, or increase the spandrels, reduce the vision glass, and then we could start looking at photovoltaic shades that capture energy, but also create shadow and block off the western sunlight coming into the building. So in the really bad part of the day, these shades actually do work. My business partner is a licensed mechanical engineer, and we work on buildings together to make them green and high-performance buildings. So this idea of the sky lobby with elevators emptying into the atrium sort of became this building. So we have these spaces, and we can turn these spaces into quite wonderful branding opportunities for the small tenants. You can come out into this space, and we could have this little wall plaque up here that says Strabela Architects, and we now look like we have 7 floors in this tall building. But we could put 4 or 5 names on the wall there, 4 or 5 small tenants that now look like they have a huge amount of space. Big value for small tenants that want to be in a building that they could brand. So the whole idea was we have internal branding for small tenants. We arrive at this floor. If this floor doesn't work out, it could be rented to someone as a restaurant, a bookstore, a conference room, a dentist, a workout space. So it's very, very flexible. And it actually allows people to come here off hours because that's how we use the elevator system. So this is a 6-story atrium. We could add extra space into it, bridges, all kinds of things. And it's deep in the building so it doesn't get direct west sun, and we have beautiful views out of the atrium. So these are just some of the images of this building. And if you look at a regular elevator system compared to this, the core almost is 30 to 40% bigger. So we get a better efficient building with this. We get a cheaper, we stack elevators, and we create a better product. So the whole idea of the twist is to line up with the neighbors. We do a lot of 3D designs to see where we're going, but this could be any shape. This could be any building. And what we have is we actually shape the outside of the building to put branding of big tenants. What we would see in the Shanghai Tower is a tenant would take one atrium and put their name on it as a big sign. The little tenants would have little signs over here, but the big tenants could put their name on the outside of the building. So what we did is we planned for 6 large tenant logos on the outside of the building. So this building type we call the next generation sky headquarters. The lobbies could be 6 stories tall in the building. You come into this lobby and then you go into either side. Depending on where your office is, fantastic space, fantastic presence, low cost, wonderful arrival spaces, and logo opportunities for small tenants. And as I see the number here, I have 12 seconds left to wrap this up. So what I'd like to do is say thank you to the conference organizers who did a great job. I'd also like to thank the sponsors who have their booth. Please go talk to them in their booths, and you might learn something. I learned something new this morning, just randomly talking to someone. Go talk to them. They love it. They're bored. You're bored. Lighten up a little bit. And I would also like to thank India. This is probably my 30th trip to India. I always enjoy coming back here. I haven't been back here in, I think, 6 years. So with that, I'd like to say, as they do in Shanghai, Shishi Nin, Shayano, Arrivederci.
Yes.
Okay.
So thank you so much, Architect Marshall Strabala. I think that was one of the most wonderful sessions we were looking forward to, and I think it was great. A beautifully delivered presentation on the convergence of art, utility, performance, core efficiency, and above all the beautiful spaces that art and architecture imbibing with structural engineering can create. So thank you so much, sir, for giving this wonderful presentation. And now I would like to call upon the Vice President South, Engineer Rajkumar, Vice President West, Preet Rai, and please kindly join us for the felicitation.
I also request Architect Chetna to join with us.
Check. Thank you, friends. Now we've got a small pleasant things to do here in this beautiful environment. This is such a wonderful conference, has been organized in such a nice environment with a lot of facilities. It is our pleasure from the headquarters to felicitate all the members of the organizing committee of ACC Hyderabad Center. As I call upon the name, may I request to please, all of them to come out to the dais, please. We have Rajkumar Kancharla, the Vice President South. We have Kanshiram A, the immediate past chairman. We have Bhim Rauti, Vice Chairman, past chairman, and we have Vice Chairman, sorry. Engineer KGC, Ramesh C, Secretary, and Mahendra Reddy, the current chairman. Then we have Narmada, the treasurer, Krishna Reddy, Rangarao, C.A. Prasad, Balamurali, Hari Krishna, Jaya Prakash, Bhim Prasad, Mahesh Reddy, Sudhakar Akkada, Sushil, Karthik Cherry, Munindra, Anush, Anvesh, Sagar, Abhishek Reddy, and Mrs. Chetana Rajkumar. I request Mahendra Reddy to please come out to the dais, please. May I request our President Vijay Sanap, along with the Vice President North and South, the felicitate on behalf of the headquarters to all the members. Please give them a very big hand, friends. What a wonderful NATCON 23. break, and we'll be back here at exactly 2:50. That is just half an hour minute, 10 to 3. Please do come back, and we are going to start the session right on time. Thank you.
It's 2:22 now, so 2 o'clock 50 minutes, that is 10 minutes to 3, we shall assemble back in the hall.
We request after lunch, we have all the speakers along with the team also, photograph is there. Please come back after lunch and we'll have a photograph. All the speakers, request all the speakers. All the speakers, yesterday's speakers, today's speakers, Darshan and everybody. Please be available after lunch. Please come back because it's late now. I'm not pressurizing you to go have a photograph now. So please let us fill out tummy and come back.
Today, I might be a celebrity, posing in front of 1,000 fans. But this fame, it has not come overnight. It all started in this state-of-the-art facility in Hyderabad. My makers looked for the best raw material, the utmost care with which they did a trial of my endurance, the uncompromising quality standard they have set before putting me here, so that I can make them proud. Strength is in my DNA. I am made from some of the finest iron ores available in the world, such as the mines of NMDC, Chhattisgarh, amongst others. My upbringing ensured that I grew up to be versatile and beautiful. My parents never compromised on anything. They always insisted that the HR coils used should be the best. They always made the best equipment available for me, hired the best professional hands to raise me. I was raised like a prodigy. Do you know, I have to go through fire to prove my worth? Like literally, 1650 degrees Celsius to be specific. It turned me into a coil that can take any shape and form. But being strong is not enough. You've got to have the perseverance, and that can only be ensured by constantly going through the grind. I can proudly say that I have successfully passed as many as 40 plus tests before making my way to this shelf. Another important thing is my power to solve multiple problems. That's why I have to take many avatars, like round, rectangular, square, etc. That's why fabricators across the country always rely on me for my performance. The result is a long fan following, which I thoroughly enjoy. After all, that's the biggest reward I ever aspired for. But that doesn't make me rest on my laurels. I strive hard every day to live up to the expectation of the changing needs of fabricators. Because I'm not an ordinary steel pipe, I am an MPL steel pipe.
Materials as raw as your imagination, that let you sketch signatures of trust. Welcome to a world you get to build. Where there's vision, there's room to play. Where there's steel, there's a way. Crafted with care, so you can bring alive your castles. Show off the towers. Romance the terrain. From blueprints to innovative designs, make them all. Get carried away. Where there's steel, there's a way. Cobbles or corners, minimal or mosaic. Make out your way. Yield the brush, for we have the canvas. Where there's steel, there's a way. Superior steel designed for your dreams. With a legacy of over 6 decades, we just have one more thing to say. Where there's MPL, there's a way.
Innovation is at the heart of our DNA. Ramco Research and Development Center, RRDC, is an independent state-of-the-art research center which develops specialized cements for specific applications for specific market segments. The NABL accredited laboratory conducts most advanced studies on the durability of concrete and has developed new products like Ramco Supercrete, Ramco Superfast, Ramco OPC 53 grade Infra and Ramco Super Plaster. RRDC guides Ramco's manufacturing units to enhance productivity and conducts training sessions to guide internal and external engineers. The sophisticated R&D lab, fully equipped with world-class technology, has scientists and concrete experts who work closely with various industry stakeholders on the potential challenges in the construction ecosystem. RRDC, creating solutions to the potential challenges in the construction ecosystem.
Rahul, what's going on?
See, Papa, this is your dockyard, this is my dockyard, and this is you, Dad. My dockyard is so strong, no one can break it. Let me show you. Oh, my dockyard broke. What if yours also breaks?
That will never happen because Dad's got magic.
Magic?
Ramco Supercrete, India's strongest cement. You will never see even a tiny crack in it and can also make Rahul's dockyard strong again. Isn't this magic?
Dad, can we please take Ramco home?
And we can build our home as well.
High-strength cement, crack-free concrete. Ramco Supercrete.
Once you see the nuclear plant, you will know how strong it is.
Rahul, what are you doing? This is my nuclear plant and this is our home. Let me see how strong it is. It's well made, even the shape is good. But there are cracks in it. Now, dangerous radiations will leak from it and destroy everything.
That will never happen because we have got Ramco Supercrete.
Ramco?
India's strongest cement. We built this nuclear plant with it. It will never develop smallest of cracks. Then how can the radiations leak?
And our home?
That too we built with Ramco Supercrete.
So can we build birds' nest with Ramco as well?
High-strength cement, crack-free concrete. Ramco Supercrete.
The oil shipment is here. Let's start the mission. We will hide this oil in our oil reserve. It is called SPR. SPR? Strategic Petroleum Reserve. It is a big tunnel, exactly like the one my dad made. Dad made? Let's go inside the tunnel with him. Inside the tunnel? That's my dad in the oil tunnel. What if the tunnel cracks? Crack? Never, because my dad has made it very strong.
It's not Dad, but Ramco Supercrete, India's strongest cement, the one which we built our home and even this oil reserve.
Oil reserve. Right now, oil from my kitchen is missing.
Not missing, Mom. Kept safely in SPR.
High-strength cement, crack-free concrete. Ramco Supercrete.
Inventor Industries Private Limited, founded by Mr. Cherukuri Satyanarayana in 1979, is a leading manufacturer of bulk drugs and button mushrooms in India. Since 2017, Inventor has ventured into the precast construction industry, taking up turnkey precast building projects and supplying precast concrete elements, including AAC blocks and precast paver blocks from their factories across Telangana, Andhra Pradesh and Odisha. With a strong belief in providing high-quality building structures on time and at the right price, Inventor Industries has recently undertaken a landmark precast building construction project for Hindustan Coca-Cola Beverages in Hyderabad, Telangana. This project aims to create a modern, digitally enabled, automated and smart factory, emphasizing the use of clean energy. Spearheading the design, engineering and execution of this project, Inventor has introduced several firsts in precast building construction, including single-height precast columns of 23 meters weighing up to 85 tons per column, and precast pre-stressed beams up to a length of 25.4 meters weighing up to 136 tons per beam. They have also implemented precast 3D volumetric lift shafts with 4 lift cores weighing up to 75 tons per element, along with various other precast elements such as stair shafts, staircases, pre-stressed slabs, U-gutters and facade walls. To meet the project's requirements, Inventor established a dedicated precast facility in Medchal and deployed state-of-the-art infrastructure for handling and lifting the large precast elements. They have 2 beds for pre-stressed beams each measuring 155 meters, and 3 beds of 155 meters each for making columns, in order to manufacture the walls and slabs for the project. Inventa utilized their second factory located in Patancheru. This facility is equipped with 5 slab beds measuring 120 meters, elematic KVT table lines, and a circulation line for wall casting. Additionally, they have 2 80-ton gantry cranes for handling at the precast factory and multiple 250-ton and 100-ton crawler cranes for erection at the construction site. This project stands as a testament to Inventa's engineering and execution prowess, showcasing their commitment to delivering innovative and high-quality precast building solutions.
Namaste, ladies and gentlemen. Crux Pre-Stressing Systems Private Limited is a renowned PT design and execution company established in 2005 and proudly serving the industry since 18 years, completed 1,000+ projects. Crux core strengths are well-optimized designs in terms of concrete usage, that is slab thicknesses, reinforcement usage and PT reinforcement. Effective usage of these 3 components will give the client overall economy while using PT in their buildings. Also, Crux is known for its service support and professional site working and timely completion by coordinating effectively with other contractors at site. Crux adopts, implements and follows stringent quality policies by checking each and every operation at site, also uses best quality materials and constantly improves the design and usage of PT hardware as per industry requirement. Crux executed and completed about 80 million square feet of IT space, about 30 million square feet of malls and multiplexes, about 30 million square feet in hospital and hospitality sector, about 30 million square feet in residential sector, and few more million square feet in industrial sector. Some of our projects are displayed here for better understanding. Novotel at Vijayawada, Radisson Hotel at Vijayawada, Taj Hotel at Vizag, KL University at Vijayawada Research Block, KL University at Vijayawada Skill Development Center, Trendset Mall Vijayawada, Centenary Mall Vijayawada, CMR at Eluru, Phoenix Guntur, Ashoka Golden Mall Kukatpalli, Malla Reddy Cine World LB Nagar, Sensation Bhumika Narsingi, Satyam Mall Amirpet, GSM Mall Chandanagar Hyderabad, TNR Mall Kompalli Hyderabad, One West Nanakram Guda, Mahavir Gateway Nanakram Guda, Vasavi GP Nanakram Guda, Naya Dallas High Tech City, Mayuri Tech Park at Vijayawada, Varun Beach Tower at Vizag, Namishri Trinity, Vasavi Atlantis, Green Space Marvel, W by DSR, DSR Classy, Lanco Hills Hyderabad, One Golden Mile Kokapet Hyderabad, Jain Capital Madhapur Hyderabad, Myscape AYDIV Nanakramguda Hyderabad, Jyoti Tech Park Nanakramguda Hyderabad, The District Nanakramguda Hyderabad, Sohini Tech Park Nanakramguda Hyderabad, Devika Rani Banjara Hills Hyderabad, Jyoti Granules Kondapur Hyderabad, Mantena Bangalore, Synergy Infra, Hyderabad. DSR Apex, Bangalore. Jyoti Valencia, Banjara Hills, Hyderabad. Ajara Hospital, Warangal. AIG, Gachibowli, Hyderabad. American Oncology, Nallagandla, Hyderabad. KIMS, Begumpet, Hyderabad. Hetero, Sanat Nagar, Hyderabad. Toshiba, Patancheru, Hyderabad. Sri Srinivasa, Banjara Hills, Hyderabad. SVC, Kondapur, Hyderabad. Fortune 1. Transfer slab for W by DSR. Transfer slab for DSR Class C. Transfer slab for Abhiram Touchstone at Vizag. We sincerely thank everyone associated with us throughout our journey and thank our clients for keeping trust with us, and we reassure everyone our best services always. Thank you very much for watching.